Hello there. I'm so glad you found your way here tonight. Right now, as you settle in, something extraordinary is happening within and around you. Trillions upon trillions of atoms are quietly holding together the fabric of your existence. The chair beneath you, the air you breathe, the very thoughts forming in your mind, all are made of these ancient, invisible building blocks. Tonight, we journey into the quiet wonder of atoms. We will explore the strange realm where particles behave like waves, where emptiness fills more space than matter, and where the rules of everyday life gently dissolve into something far more mysterious. The atom was once imagined as a tiny solid sphere, indivisible and eternal. But as scientists looked closer, they discovered a hidden world of electrons, protons, neutrons, and forces that defy our ordinary understanding. At this scale, certainty gives way to probability, and particles dance in patterns governed by quantum rules. There is no test at the end, no rush, no urgency, just the gentle unfolding of one of nature's deepest secrets to carry you softly towards sleep. So let your breathing slow, let your thoughts grow quiet, and allow yourself to drift into the peaceful wonder of the atomic world. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the remarkable structures that compose everything you have ever seen or touched. Either way, this space is for you. There is something deeply calming about contemplating atoms. Every breath you take contains more atoms than there are stars in the observable universe. Every heartbeat depends on the precise dance of electrons through your cells. The story of the atom is the story of existence itself. You are part of that story. The atoms in your body were forged in ancient stars, scattered across the cosmos, and gathered together over billions of years to form the person listening to these words tonight. You are made of star stuff, arranged in patterns that can wonder about their own origins. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in, let the weight of the day drift away, and let us begin with the first of many quiet truths about the atoms that make up everything. Atoms are patient beyond measure. They exist for billions of years, cycling through stars and planets, oceans and organisms. They form and reform into countless arrangements, carrying the history of the universe within their structure. And yet, within all that vastness, there are moments of stunning change, nuclear reactions that release unimaginable energy, quantum leaps that happen in instants too brief to measure, bonds that form and break in the chemistry of life. Tonight, we will wander through this magnificent, invisible world. We will meet the particles that compose all matter. We will discover the forces that hold everything together. And we will uncover truths about atoms that may surprise even the most curious minds. But there is no hurry. The atoms around you have been waiting since the beginning of time. They can continue their quiet existence while you rest. Let us begin with what the atom truly is. Atoms are mostly empty space, with nearly all mass concentrated in the nucleus. If you could zoom into any atom, you would find something quite surprising. The vast majority of its interior is empty space, with almost nothing between the outer electron cloud and the tiny central nucleus. That nucleus contains nearly all of the atom's mass, packed into a region so incredibly small that it occupies roughly 1/1,000,000th of the atom's total volume. To put this in perspective, if an atom were the size of a football stadium, the nucleus would be no larger than a single pea resting at the center of the pitch. The electrons that surround it exist at incomprehensible distances relative to the nucleus, drifting through their probability zones like faint whispers of charge. This means the solid world you experience, every wall, every table, every part of your own body, is overwhelmingly made of emptiness. The sensation of solidity comes not from matter filling space, but from electromagnetic forces pushing back whenever atoms approach one another. It is one of the gentlest paradoxes of nature that what feels most real is almost entirely nothing at all. The word atom comes from an ancient Greek term meaning uncuttable. The ancient Greek philosophers wondered what would happen if you kept cutting a piece of matter in half again and again. Eventually, they reasoned, you would reach a point where the fragment could not be divided any further. The philosopher Democritus gave this ultimate particle the name atomos, meaning uncuttable or indivisible. For over 2,000 years, this concept remained a philosophical idea rather than a scientific one, debated by thinkers but never tested in a laboratory. It was not until the early 1800s that scientists began gathering experimental evidence that matter truly was made of discrete units. John Dalton proposed his atomic theory based on the way elements combined in fixed ratios during chemical reactions. The name atom stuck even though we now know that atoms can indeed be split, releasing tremendous energy in the process. The word itself carries the memory of an ancient insight, a quiet reminder that the deepest questions about the nature of matter were first asked not with instruments, but with simple human curiosity and wonder. A single grain of sand contains more atoms than there are grains of sand on Earth. The numbers that describe the atomic world can feel almost impossible to grasp. A single grain of sand, small enough to rest on your fingertip without you even noticing, contains roughly 50 quintillion atoms packed tightly together. Meanwhile, the total number of grains of sand across all the beaches, deserts, and riverbeds on Earth is estimated to be somewhere around 7 quintillion. This means that one tiny grain holds several times more atoms within it than all the grains of sand that exist on our entire planet. It is a comparison that quietly reveals just how small atoms truly are and how many of them are needed to build even the simplest visible object. Every breath you take draws in roughly 10 sextillion atoms of various elements, each one far too small for any human eye to see. These staggering numbers are part of everyday reality, hidden in plain sight within every object you touch, every surface you rest upon, and every drop of water you drink. The sheer abundance of atoms is one of the quiet marvels that surrounds you always. Electrons do not orbit the nucleus like planets, but exist as probability clouds. Early models of the atom imagined electrons circling the nucleus in neat, planet-like orbits, much like a miniature solar system. It was a tidy picture, but nature had something far more mysterious in mind. Quantum mechanics revealed that electrons do not follow fixed paths at all. Instead, they exist as diffuse clouds of probability spread around the nucleus, and each point in that cloud represents a likelihood of finding the electron there at any given moment. These clouds, called orbitals, come in a variety of beautiful shapes, from simple spheres to more complex lobed and ring-like forms. The shape of each orbital depends on the energy and quantum numbers assigned to that electron. You can never say exactly where an electron is at any instant, only where it is most likely to be. This probabilistic nature is not a limitation of our instruments, but a fundamental feature of reality at the quantum scale. It is a gentle reminder that the universe, at its deepest level, operates on rules very different from our everyday experience of certainty and solid ground. The nucleus was discovered through an experiment involving gold foil and alpha particles. In 1911, Ernest Rutherford and his colleagues performed one of the most famous experiments in the history of science. They fired a beam of alpha particles, which are tiny positively charged fragments at an extremely thin sheet of gold foil. Most of the particles pass straight through as if the foil were barely there, which was expected if atoms were mostly empty space. But a small number of particles bounced back at sharp angles, and some even reversed direction entirely. Rutherford later said it was as if you had fired a cannon shell at a piece of tissue paper and it came back and hit you. This startling result revealed that atoms contain a dense, positively charged core, which he named the nucleus. The experiment overturned the earlier plum pudding model, which imagined positive charge spread evenly throughout the atom. Instead, the atom was revealed to be mostly void, with a tiny but massive center holding nearly all the weight. It was a quiet revolution in our understanding of matter, born from a simple question and a sheet of gold thinner than a whisper. Protons and neutrons are themselves made of smaller particles called quarks. For a long time, protons and neutrons were considered the smallest building blocks of the atomic nucleus, but deeper investigation revealed that they too have an inner structure. Each proton is made of 3 quarks, specifically 2 up quarks and 1 down quark, bound together by the strong nuclear force. Neutrons also contain 3 quarks, but in a different arrangement, 2 down quarks and 1 up quark. Quarks are among the most fundamental particles known to physics, and they come in 6 varieties, whimsically named up: down, charm, strange, top, and bottom. No one has ever observed a single quark in isolation, because the force binding them together actually grows stronger as you try to pull them apart, a phenomenon known as confinement. This means quarks are forever locked within larger particles, hidden from direct view. The gluons that carry the strong force between quarks themselves carry color charge, making the interior of a proton a seething, dynamic environment. It is humbling to consider that even the components of the nucleus have their own hidden depths waiting to be explored. The strong nuclear force is the most powerful force in the universe at short ranges. Of the 4 fundamental forces of nature, the strong nuclear force stands apart as the mightiest. It is roughly 100 times stronger than the electromagnetic force and many trillions of times stronger than gravity. However, its power operates only at incredibly short distances, typically within the confines of an atomic nucleus. At these tiny scales, the strong force binds quarks together inside protons and neutrons, and then holds those protons and neutrons tightly within the nucleus itself. Without this force, the positively charged protons in a nucleus would fly apart from their mutual electromagnetic repulsion in a fraction of a second. The strong force is carried by particles called gluons, which shuttle back and forth between quarks at nearly the speed of light. Despite its immense strength, the strong force drops off so rapidly with distance that it has no noticeable effect beyond the nucleus. This is why you do not feel it in everyday life, even though it is the very force that holds together every atom in your body and every atom in the world around you tonight. Atoms of the same element always have the same number of protons. What makes gold different from iron or oxygen different from carbon is simply the number of protons sitting inside the nucleus. Every atom of hydrogen has exactly 1 proton. Every atom of helium has 2. Every atom of carbon has 6. This number, called the atomic number, is the defining identity of each element. If you were to somehow add or remove a proton from a nucleus, you would literally transform one element into another, a process that does occur in nuclear reactions and inside stars. The number of neutrons can vary without changing the element, and the number of electrons can shift as atoms gain or lose charge. But the proton count is sacred to the identity of that atom. This elegant system means that the entire diversity of matter in the universe, from the air you breathe to the stars you see, comes down to how many protons are gathered in each nucleus. It is a beautifully simple principle underlying a staggeringly complex world, and it all traces back to that one small number sitting quietly at the heart of every atom. Isotopes are atoms with the same number of protons, but different numbers of neutrons. While the number of protons defines which element an atom belongs to, the number of neutrons can vary from one atom to the next. These different versions are called isotopes. For example, most carbon atoms have 6 neutrons, making them carbon-12. But some carbon atoms carry 7 neutrons, forming carbon-13, and a rare few have 8 neutrons, creating carbon-14. All three are still carbon, behaving almost identically in chemical reactions, but their nuclear properties can differ dramatically. Some isotopes are perfectly stable, sitting quietly for the entire age of the universe. Others are radioactive, slowly releasing energy as their nuclei transform into more stable arrangements. This property makes isotopes extraordinarily useful. Carbon-14 decays at a known rate, allowing scientists to determine the age of ancient organic materials. Other isotopes serve as tracers in medicine, helping doctors observe processes inside the living body without surgery. The gentle variation of neutron numbers within the same element creates a rich tapestry of atomic behavior, adding yet another layer of quiet complexity to the world of the very small. The electron cloud of an atom determines most of its chemical properties. Although the nucleus holds nearly all of an atom's mass, it is the electrons on the outside that determine how the atom interacts with the world. The arrangement of electrons around an atom, particularly those in the outermost shell, governs whether it will bond with other atoms, how strongly, and in what patterns. Atoms with similar outer electron arrangements tend to behave alike in chemical reactions, which is why elements in the same column of the periodic table share similar properties. For instance, the alkali metals all have a single electron in their outer shell, making them highly reactive and eager to form bonds. Noble gases, on the other hand, have their outer shells completely filled, making them remarkably inert and content to exist alone. The shape and energy of the electron cloud also influence how atoms absorb and emit light, which is why different elements produce different colors when heated. Every color you see in a firework display comes from the unique electron arrangement of a particular element. The chemical richness of the entire natural world traces back to these quiet distributions of charge surrounding each nucleus. Atoms can exist in excited states when electrons absorb energy and jump to higher levels. When an atom absorbs just the right amount of energy, one of its electrons can leap from its usual position to a higher energy level further from the nucleus. The atom is then said to be in an excited state, carrying more energy than it normally would. This extra energy is temporary, however, and the electron will eventually fall back down to a lower level, releasing the absorbed energy as a photon of light. The color of that photon depends on the exact difference in energy between the two levels, which is why each element emits its own unique set of colors. This behavior is the reason neon signs glow in vivid shades, why sodium street lamps cast an orange hue, and why astronomers can identify elements in distant stars just by studying their light. The excited state lasts only a tiny fraction of a second in most cases, yet in that fleeting moment, the atom carries a quiet potential energy within it. When the electron returns to its resting state, the photon it releases travels outward at the speed of light, carrying a small parcel of the atom's story into the world around it. The quantum leap describes an electron moving between energy levels without passing through the space between. In the quantum world, an electron does not gradually drift from one energy level to another. Instead, it makes what physicists call a quantum leap, appearing at the higher or lower level instantaneously without ever occupying the space in between. There is no journey, no smooth transition, no halfway point. The electron simply ceases to exist at one level and appears at another, all in a time interval too brief to measure. This idea troubled many early scientists because it defied every intuition built from observing the everyday world, where objects always pass through intermediate positions when they move. Yet decades of experiments have confirmed that quantum leaps are real and fundamental to how atoms behave. Every time an atom emits or absorbs light, a quantum leap has occurred within it. The phrase has entered everyday language as a metaphor for a sudden, dramatic change, though in physics, the actual distances involved are incomprehensibly small. It is one of the quieter marvels of atomic physics, a reminder that the rules governing the universe's tiniest components are profoundly different from those we encounter in our daily lives. Heisenberg's uncertainty principle means you cannot know both position and momentum of a particle precisely. One of the most fundamental ideas in quantum mechanics is that certain pairs of properties cannot be measured simultaneously with perfect accuracy. Werner Heisenberg discovered that the more precisely you determine the position of a particle like an electron, the less precisely you can know its momentum, and vice versa. This is not because of any flaw in our instruments or techniques. It is a built-in feature of the universe, woven into the very fabric of reality at the quantum scale. The uncertainty principle arises because particles also behave as waves, and a wave does not have a single definite position or a single definite momentum. It is always spread out to some degree. The more you confine a wave to a specific location, the more its momentum becomes uncertain. This principle places a gentle but absolute limit on what can ever be known about a quantum particle at any given moment. It quietly reminds us that the universe retains a measure of mystery no matter how carefully we look. At the smallest scales of nature, complete knowledge is not merely difficult, but fundamentally impossible. Wave-particle duality means that particles like electrons can behave as both waves and particles. One of the most puzzling discoveries in physics is that matter and light do not fit neatly into a single category. Electrons, photons, and other quantum entities can behave as particles in some experiments and as waves in others. When electrons travel through a crystal, they diffract and interfere just like waves passing through a narrow opening. Yet when they strike a detector, they arrive as individual points, just like tiny particles. This dual nature is not a contradiction, but a fundamental feature of the quantum world. It simply means that our everyday categories of wave and particle are too limited to capture what quantum objects truly are. The wave aspect describes the probability of where a particle might be found, while the particle aspect describes what actually registers when a measurement is made. Louis de Broglie first proposed that all matter has a wavelength, and experiments quickly confirmed this startling idea. Both light and matter share this peculiar duality, and it lies at the heart of everything from electron microscopes to the behavior of atoms in your body right now as you rest. The double-slit experiment reveals that particles create interference patterns like waves. The double-slit experiment is often called the most beautiful experiment in physics. When a beam of particles, such as electrons or photons, is fired at a barrier with two narrow slits, something remarkable happens. Instead of creating two simple clusters on the screen behind the barrier, the particles build up an interference pattern of alternating bright and dark bands, exactly as waves would. Even more astonishing, this pattern emerges even when particles are sent through one at a time, as if each individual particle passes through both slits simultaneously and interferes with itself. However, the moment you place a detector at the slits to observe which path the particle takes, the interference pattern vanishes and the particles behave like ordinary objects passing through one slit or the other. This experiment reveals that observation itself changes the outcome at the quantum level. It has been repeated countless times with electrons, photons, atoms, and even larger molecules, and the result is always the same. The double-slit experiment gently demonstrates that the quantum world does not play by the rules of our everyday experience. Electrons in atoms are described by mathematical wave functions rather than fixed orbits. In the early days of atomic science, electrons were imagined traveling along neat circular paths around the nucleus, like planets around a star. But the development of quantum mechanics replaced this tidy picture with something far more subtle. Electrons are now described by mathematical objects called wave functions, which assign a probability amplitude to every possible location around the nucleus. The square of the wave function at any point gives the probability of finding the electron there. These wave functions define shapes known as orbitals, which can be spherical, dumbbell-shaped, or more complex, depending on the electron's energy and angular momentum. An electron does not trace a path through space. Instead, it exists as a spread-out distribution of possibilities until a measurement pins it down. The wave function contains all the information that can ever be known about that electron's state. It is a mathematical description of possibility itself, and it works with astonishing precision to predict how atoms behave. The shift from fixed orbits to wave functions was one of the greatest changes in how humans understand nature's smallest structures. The Schrödinger equation governs how quantum states evolve over time. In 1926, Erwin Schrödinger wrote down an equation that would transform our understanding of the atomic world. The Schrödinger equation describes how the wave function of a quantum system changes as time passes. It is the quantum equivalent of Newton's laws of motion, but instead of predicting exact trajectories, it predicts how probabilities evolve. Given the wave function at one moment, the equation tells you what the wave function will look like at any future moment, as long as no measurement interrupts the process. The equation applies to single particles, to atoms, to molecules, and in principle to any quantum system, regardless of its complexity. Its solutions reveal the allowed energy levels of atoms, the shapes of electron orbitals, and the probabilities of transitions between states. The Schrödinger equation has been tested against experiment countless times and has never been found to fail within its domain. It is one of the most successful equations in all of physics, quietly governing the behavior of every atom in the universe, including every atom resting peacefully within you tonight. Superposition allows quantum particles to exist in multiple states simultaneously. In ordinary life, a coin is either heads or tails, a light is either on or off. But in the quantum world, particles can exist in a combination of states all at once, a condition called superposition. An electron can simultaneously spin in two opposite directions. A photon can travel along two different paths at the same time. This is not an abstract trick of mathematics, but a physical reality confirmed by countless experiments over nearly a century. Superposition is what allows the interference patterns in the double-slit experiment, because the particle must be in some sense passing through both slits simultaneously. The key is that superposition persists only as long as the system remains undisturbed. The moment a measurement is made, the particle appears in just one definite state, and the superposition vanishes. This transition from many possibilities to a single outcome is one of the deepest mysteries in physics. Superposition lies at the heart of quantum computing, quantum cryptography, and many other emerging technologies that promise to reshape the future. It is a gentle truth about the universe that coexists quietly with the certainty of our everyday world. Measuring a quantum particle causes its wave function to collapse into a single state. Before a measurement is made, a quantum particle exists as a spread of possibilities described by its wave function. It might be here or there, spinning this way or that, each option weighted by a certain probability. But the instant an observation occurs, something dramatic happens. The wave function collapses, and the particle snaps into one definite state. All the other possibilities simply disappear, and only the measured reality remains. This process is one of the most debated topics in quantum physics, because the equations of quantum mechanics do not explain how or why the collapse happens. The Schrödinger equation describes smooth, continuous evolution, yet measurement produces a sudden, irreversible change. Some physicists believe the collapse is a real physical process, while others think it is merely a change in our knowledge of the system. The debate has spawned numerous interpretations of quantum mechanics, each offering a different perspective on what happens during that mysterious moment. What everyone agrees on, however, is that measurement fundamentally changes the quantum world. It is a quiet but powerful reminder that at the smallest scales, the act of looking is never passive. Quantum entanglement links particles so that measuring one instantly affects the other. When two particles become entangled, they share a quantum connection that persists no matter how far apart they are separated. Measuring a property of one entangled particle instantly determines the corresponding property of the other, even if they are on opposite sides of the universe. Albert Einstein famously called this phenomenon spooky action at a distance, finding it deeply troubling because it seemed to violate the principle that nothing can travel faster than light. Yet decades of experiments have confirmed that entanglement is real and that the correlations between entangled particles are stronger than anything classical physics can explain. Crucially, no usable information actually travels between the particles during this process, so it does not break the cosmic speed limit. The connection is subtler than that, a shared quantum state rather than a signal. Entanglement is now being harnessed in cutting-edge technologies such as quantum communication and quantum key distribution, where it helps create encryption methods that are theoretically unbreakable. It remains one of the most fascinating aspects of the quantum world, a quiet bond between particles that defies ordinary intuition and gently hints at the deeper unity underlying all of nature. The Higgs field gives mass to fundamental particles throughout the universe. Mass might seem like the most basic property of matter, but its origin turns out to be deeply connected to a field that permeates all of space. The Higgs field was first proposed in 1964 as a way to explain why some fundamental particles have mass while others, like photons, do not. The idea is that certain particles interact with this invisible field as they move through space, and that interaction is what gives them their mass. Particles that interact strongly with the Higgs field are heavy, while those that interact weakly are light. A particle that does not interact with the field at all remains massless. The Higgs boson, discovered in 2012 at the Large Hadron Collider, is the quantum excitation of this field, the particle that proves the field exists. Without the Higgs field, electrons would be massless and could not be captured into orbits around nuclei. Atoms as we know them would not form, chemistry would not exist, and neither would you. The Higgs field quietly gives substance to the material world, working invisibly in every corner of the universe to grant particles the mass they carry. Photons are massless particles that carry the electromagnetic force. Every time you see light, feel warmth from the sun, or use a mobile phone, you are experiencing the work of photons. A photon is the quantum of the electromagnetic field, the smallest possible unit of light or electromagnetic radiation. Photons have no mass and always travel at the speed of light in a vacuum, roughly 300,000 kilometers per second. They are the carriers of the electromagnetic force, which is responsible for holding electrons in their orbits around nuclei, binding atoms together in molecules, and governing virtually all of the chemistry and biology that fills everyday life. When an electron in an atom drops from a higher energy level to a lower one, a photon is emitted carrying the exact difference in energy away at the speed of light. Photons come in a vast range of energies, from the gentle radio waves that carry music to your ears to the powerful gamma rays released in nuclear reactions. Despite being massless, photons carry momentum and energy, and they can exert a tiny push on objects they strike. They are among the most abundant particles in the universe, outnumbering atoms by roughly 1 billion to 1, silently filling space with their quiet energy. Gluons hold quarks together inside protons and neutrons. Deep within every proton and neutron, a ceaseless exchange of particles keeps the quarks bound together with extraordinary strength. These binding particles are called gluons, named for their role as the glue of the atomic nucleus. Gluons carry the strong nuclear force between quarks, constantly being emitted and absorbed in a dizzying dance that happens on timescales far shorter than anything we can directly observe. Unlike photons, which carry the electromagnetic force but have no electric charge themselves, gluons carry the strong force's equivalent of charge, known as color charge. This means gluons can interact with each other as well as with quarks, making the interior of a proton an extraordinarily dynamic environment. There are 8 different types of gluon, each carrying a different combination of color charge. The energy contained in the gluon field inside a proton actually accounts for most of the proton's mass, far more than the quarks themselves contribute. When physicists say mass comes from energy, this is one of the most vivid examples. The gluons buzzing within every nucleus in your body represent one of the most powerful forces in nature, working silently to hold matter together. The weak nuclear force is responsible for radioactive beta decay. Among the 4 fundamental forces, the weak nuclear force is perhaps the least familiar, yet its effects shape the universe in profound ways. The weak force governs a type of radioactive decay called beta decay, in which a neutron inside a nucleus transforms into a proton while emitting an electron and an antineutrino. This process changes one element into another, allowing atoms to slowly transmute over time. The weak force is carried by 3 massive particles known as the W+, W-, and Z bosons. Because these carriers are so heavy, the force they transmit operates only at distances even shorter than the strong nuclear force, around 1,000th the diameter of a proton. Despite its short range, the weak force plays a crucial role in the life cycle of stars. In the Sun's core, the weak force enables the first step of hydrogen fusion, converting protons into neutrons so that helium can eventually form. Without this step, the Sun would not shine and life on Earth could not exist. The weak force is a quiet architect of cosmic change, working on the smallest of scales to influence the grandest of outcomes. Virtual particles constantly appear and disappear in the quantum vacuum. Even in the emptiest regions of space, something extraordinary is happening. The quantum vacuum is not truly empty, but alive with activity, as pairs of virtual particles spontaneously pop into existence and then vanish again in unimaginably short intervals. These fleeting particles borrow energy from the vacuum for a brief moment, existing just long enough to influence the world around them before disappearing again. This process is permitted by the uncertainty principle, which allows temporary violations of energy conservation, provided they happen quickly enough. Virtual particles are not merely theoretical. Their effects have been measured with great precision. They alter the energy levels of hydrogen atoms by a tiny amount known as the Lamb shift, and they contribute to the magnetic moment of the electron in ways that match experimental results to extraordinary accuracy. The quantum vacuum seethes with these ghostly fluctuations everywhere in the universe, from the depths of intergalactic space to the interior of every atom in your body. It is a humbling thought that even perfect emptiness is never truly still, that the universe hums with quiet activity at scales far too small for human senses to perceive. The Casimir effect demonstrates that empty space is never truly empty. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged metallic plates placed very close together in a vacuum would experience a tiny attractive force pulling them toward each other. This force, now known as the Casimir effect, arises because the quantum vacuum between the plates can only support certain wavelengths of virtual particle fluctuations, while the space outside the plates has no such restriction. The resulting imbalance creates a measurable pressure that gently pushes the plates together. The effect was confirmed experimentally in 1997, providing one of the most direct demonstrations that the quantum vacuum is not empty at all, but filled with energy. The Casimir effect is incredibly small under ordinary conditions, yet at microscopic scales it becomes significant and must be accounted for in the design of tiny mechanical devices. It elegantly shows that the fabric of space itself has properties and structure, even when no conventional matter or energy is present. The Casimir effect is a gentle whisper from the quantum world, reminding us that the void between atoms and between stars is far richer and more interesting than simple emptiness. Quantum tunneling allows particles to pass through barriers they classically could not. Imagine rolling a ball toward a hill that is too tall for the ball to climb over. In everyday life, the ball would simply roll back. But in the quantum world, there is always a small probability that a particle will appear on the other side of the barrier, even though it never had enough energy to cross it. This phenomenon is called quantum tunneling, and it is a direct consequence of the wave-like nature of quantum particles. The wave function of a particle does not stop abruptly at a barrier. Instead, it decays exponentially through the barrier, and if the barrier is thin enough, a portion of the wave emerges on the other side. The probability of tunneling depends on the particle's energy and the barrier's thickness and height. Tunneling is not a rare curiosity. It plays essential roles in many physical processes. Radioactive alpha decay occurs because alpha particles tunnel out of the nucleus. The flash memory in electronic devices relies on electrons tunneling through thin insulating layers. Every day, quantum tunneling governs countless processes in technology and nature, working silently at the atomic scale to cross barriers that classical physics insists are impassable. Nuclear fusion in stars relies on quantum tunneling to overcome repulsion between protons. The sun and all the stars in the night sky shine because of nuclear fusion, the process that fuses lighter atomic nuclei together to form heavier ones while releasing tremendous energy. But there is a problem. Protons carry positive charge and repel each other with enormous force. For two protons to fuse, they must get close enough for the strong nuclear force to take over, yet their mutual repulsion creates an energy barrier that the protons in a star's core do not classically have enough energy to overcome. This is where quantum tunneling becomes essential. The wave-like nature of protons allows a small but significant fraction of them to pass through the repulsive barrier and reach each other, triggering fusion. Without tunneling, the temperatures inside the sun would be far too low for fusion to occur at any meaningful rate. The sun would be dark, and the universe would be a cold, lifeless place. Quantum tunneling is therefore responsible for the light that warms the Earth, the energy that drives photosynthesis, and ultimately the existence of life itself. Every ray of sunshine carries the signature of this quiet quantum miracle at its heart. The periodic table arranges elements by the number of protons in their atoms. The periodic table is one of the most elegant organizational systems in all of science. It arranges every known element in order of increasing atomic number, which is simply the count of protons in each atom's nucleus. Hydrogen with 1 proton comes first. Helium with 2 comes next. The table continues through increasingly heavy elements, all the way up to oganesson with 118 protons. But the genius of the periodic table lies in its rows and columns. Elements in the same column tend to share similar chemical properties because they have similar outer electron configurations. The alkali metals on the far left are all highly reactive. The noble gases on the far right are all remarkably inert. This repeating pattern is what gives the table its name, the periodic table, because properties recur at regular intervals. Dmitri Mendeleev first published his version in 1869, and he boldly left gaps for elements that had not yet been discovered. When those elements were later found, they fitted his predictions with remarkable accuracy. The periodic table remains the map of the elements, a quiet guide to the building blocks of everything around you. Chemical bonds form when atoms share or transfer electrons between their outer shells. Atoms rarely exist alone in nature. Instead, they combine with other atoms through chemical bonds, creating molecules and materials with properties quite different from the individual elements. The driving principle behind bonding is that atoms tend to seek the most stable arrangement of their outer electrons. When 2 atoms approach each other, their outer electron clouds can interact in ways that lower the total energy of the system, creating a bond. In some cases, atoms share electrons, each contributing 1 or more to a common pool held between them. In other cases, one atom donates electrons to another, producing charged particles called ions that are held together by their opposite charges. The type of bond that forms depends on the nature of the atoms involved, particularly how tightly they hold onto their outer electrons. Chemical bonds are what build water from hydrogen and oxygen, what construct the proteins and DNA in your cells, and what hold together the minerals in the rocks beneath you. Without chemical bonding, matter would exist only as isolated atoms drifting through space. Every material you have ever touched owes its existence to the quiet exchange of electrons between neighboring atoms. Covalent bonds involve atoms sharing pairs of electrons equally. When 2 atoms have similar tendencies to attract electrons, they often form a bond by sharing 1 or more pairs of electrons between them. This type of bond is called a covalent bond, and it is one of the most common in nature. In a covalent bond, the shared electrons spend their time in the space between the 2 nuclei drawn toward both. This shared cloud of electrons holds the atoms together, creating a stable molecule. A single covalent bond involves 1 shared pair of electrons, but double and triple bonds are also possible when atoms share 2 or 3 pairs, respectively. The oxygen molecules in the air you breathe are held together by a double covalent bond, while nitrogen molecules are held by a remarkably strong triple bond. Covalent bonds are the foundation of organic chemistry, linking carbon atoms into chains and rings that form the backbone of all living molecules, from simple sugars to the vast strands of DNA. The strength and directionality of covalent bonds give molecules their specific shapes, which in turn determine their functions. Life itself is built upon the quiet sharing of electrons between atoms that choose to hold on together. Ionic bonds form when one atom transfers electrons to another, creating charged ions. Sometimes atoms do not share electrons equally. Instead, one atom gives up electrons entirely while the other takes them in. The atom that loses electrons becomes a positively charged ion, while the atom that gains them becomes negatively charged. The electrostatic attraction between these opposite charges creates a strong bond known as an ionic bond. Table salt is one of the most familiar examples. A sodium atom donates one electron to a chlorine atom, producing sodium and chloride ions that lock together in a rigid crystal lattice. Ionic compounds tend to form hard, brittle crystals with high melting points because the electrostatic forces holding the ions in place are very strong and extend in all directions. When dissolved in water, however, the ions separate and can move freely, which is why salt water conducts electricity while a dry salt crystal does not. Ionic bonding is the reason your nerves can send electrical signals, because the movement of sodium and potassium ions across cell membranes generates the tiny currents that carry information through your body. These bonds between giving and receiving atoms quietly support both the structure of minerals and the chemistry of life. Metallic bonds allow electrons to flow freely, creating electrical conductivity. Metals have a distinctive way of bonding that sets them apart from other materials. In a metallic bond, the outer electrons of each atom are not held tightly by any single nucleus, but instead become part of a shared sea of electrons that flows freely throughout the entire metal structure. The metal atoms sit as positive cores held in place by their mutual attraction to this communal electron cloud. This arrangement explains many of the properties that make metals so useful. The free-flowing electrons carry electrical current with ease, which is why copper and aluminum are used in wiring. They also conduct heat efficiently, transferring vibrational energy quickly through the electron sea. The ability of the electron cloud to shift and redistribute under stress allows metals to be hammered into sheets or drawn into wires without breaking, properties known as malleability and ductility. Metallic bonding is also responsible for the luster of polished metal surfaces because the free electrons can absorb and re-emit light across a broad range of wavelengths. From the iron in bridges to the gold in jewelry, metallic bonds quietly provide the foundation for much of human civilization's infrastructure and craftsmanship. The electron configuration of an atom determines its reactivity and bonding behavior. Every atom arranges its electrons in a specific pattern of energy levels and subshells, and this arrangement, called the electron configuration, dictates how the atom interacts with the world. Electrons fill the lowest available energy levels first, gradually occupying higher ones as more electrons are added. The outermost electrons, known as valence electrons, are the ones that participate in chemical bonding and reactions. An atom with one or two valence electrons tends to lose them easily, forming positive ions and bonding with atoms that readily accept electrons. An atom with nearly a full outer shell tends to gain electrons, forming negative ions. An atom with a half-filled or fully filled outer shell behaves quite differently from one that is just one electron short. This simple principle explains why lithium, sodium, and potassium all react vigorously with water, while helium, neon, and argon remain serenely unreactive. The electron configuration is like a quiet blueprint that determines each element's personality, governing its tendency to bond, its preferred partners, and the types of molecules it can form. Understanding this arrangement is the key to understanding all of chemistry. Noble gases have complete outer electron shells, making them chemically stable. On the far right of the periodic table sits a family of elements that are among the most serene in all of chemistry. Helium, neon, argon, krypton, xenon, and radon are the noble gases, and they share one defining trait. Their outer electron shells are completely filled. This full shell configuration means they have no tendency to gain, lose, or share electrons with other atoms. As a result, noble gases are remarkably unreactive under ordinary conditions, existing as lone atoms rather than bonding into molecules. For decades, chemists believed noble gases could not form compounds at all. It was not until 1962 that Neil Bartlett demonstrated that xenon could be coaxed into bonding with highly reactive fluorine under extreme conditions. Even so, noble gas compounds remain rare and exotic. In everyday life, the stability of noble gases makes them incredibly useful. Helium fills balloons and cools superconducting magnets. Neon glows in advertising signs. Argon fills the sealed space inside double-glazed windows, providing insulation precisely because it is so inert. The noble gases are nature's example of quiet contentment, atoms so perfectly complete that they have no need to form bonds with the world around them. Radioactive atoms decay by emitting particles or energy to become more stable. Some atomic nuclei are inherently unstable, carrying more energy than they can comfortably hold. Over time, these nuclei release that excess energy by emitting particles or radiation, transforming into different, more stable configurations. This process is called radioactive decay, and it happens spontaneously without any external trigger. There are several types of decay. In alpha decay, the nucleus releases a cluster of 2 protons and 2 neutrons, forming a helium nucleus. In beta decay, a neutron transforms into a proton while emitting an electron and an antineutrino. In gamma decay, the nucleus simply releases a burst of high-energy electromagnetic radiation. Each type of decay changes the atom in a specific way, sometimes transforming it into an entirely different element. The rate of decay varies enormously between different isotopes, from fractions of a second for the most unstable to billions of years for others. Radioactive decay is the source of natural background radiation that has existed since the Earth formed. It warms the planet's interior, drives geological processes, and provides the basis for radiometric dating. It is nature's quiet mechanism for returning unstable matter to a state of rest. Half-life measures the time for half of a radioactive sample to decay. Every radioactive isotope has a characteristic pace at which its atoms decay, and this pace is described by a quantity called the half-life. The half-life is the time it takes for exactly half of a given sample of radioactive atoms to undergo decay. After one half-life, half the original atoms remain. After 2 half-lives, 1/4 remains. After 3, 1/8, and so on. The process continues indefinitely, with the number of remaining radioactive atoms halving at each interval. Half-lives vary enormously across different isotopes. Some exotic isotopes last for only fractions of a second before decaying, while others persist for billions of years. Uranium-238, for instance, has a half-life of about 4.5 billion years, which is roughly the age of the Earth itself. This means that about half of the uranium present when our planet formed is still here, slowly decaying in rocks deep beneath the surface. Carbon-14 has a half-life of about 5,730 years, making it ideal for dating archaeological finds up to tens of thousands of years old. The concept of half-life brings a gentle mathematical order to the randomness of radioactive decay. Carbon dating uses the decay of carbon-14 to determine the age of organic materials. Every living organism absorbs carbon from its environment, including a tiny proportion of the radioactive isotope carbon-14. While the organism is alive, the ratio of carbon-14 to ordinary carbon-12 remains roughly constant because new carbon is continually taken in. But once the organism dies, it stops absorbing carbon, and the carbon-14 within it begins to decay without being replaced. By measuring how much carbon-14 remains in a sample and comparing it to the amount expected in a living organism, scientists can calculate how long ago the organism died. This technique known as radiocarbon dating, was developed by Willard Libby in the late 1940s and earned him a Nobel Prize. It has been used to date ancient wood, bone, cloth, and other organic materials with remarkable accuracy, revealing the ages of archaeological treasures and ancient civilizations. The method works reliably for materials up to roughly 50,000 years old, beyond which too little carbon-14 remains to measure accurately. Radiocarbon dating is a quiet gift from the atomic world, allowing us to reach into the past and measure the flow of time through the patient decay of individual atoms. Uranium atoms can split apart in fission reactions, releasing enormous energy. Nuclear fission occurs when a heavy atomic nucleus splits into two or more lighter nuclei, releasing a tremendous burst of energy in the process. Uranium-235 is one of the best-known fissile materials. When a slow-moving neutron strikes a uranium-235 nucleus, the nucleus becomes unstable and splits apart, typically producing two medium-sized nuclei, 2 or 3 additional neutrons, and a large amount of energy. Those released neutrons can then strike other uranium nuclei, causing them to split as well in what is known as a chain reaction. If the chain reaction is controlled carefully, the energy can be harnessed to generate electricity in nuclear power plants, which produce no direct carbon emissions. If the reaction is uncontrolled, the result is a nuclear explosion of devastating power. The energy released in fission comes from the conversion of a small amount of mass into energy, as described by Einstein's famous equation. A single kilogram of uranium fuel contains roughly the same energy as 2.5 million kilograms of coal. Fission is a profound demonstration that the quiet structure of an atom conceals an almost unimaginable reservoir of energy waiting to be released. Einstein's equation E equals mc squared explains why nuclear reactions release so much energy. In 1905, Albert Einstein published a short paper containing what would become the most famous equation in all of physics: energy equals mass times the speed of light squared. This deceptively simple expression reveals that mass and energy are two forms of the same thing, and that a tiny amount of mass can be converted into an enormous amount of energy because the speed of light is such a large number. When it is squared, the conversion factor becomes roughly 90 quadrillion in standard units. This means that even a paperclip, if its mass could be entirely converted to energy, would release an explosion rivaling a nuclear weapon. In practice, nuclear reactions convert only a small fraction of the involved mass into energy, yet even that fraction produces staggering results. Fission and fusion reactions both release energy because the products weigh slightly less than the original materials, and the missing mass has been transformed into energy. Einstein's equation quietly underpins our understanding of why stars shine, why nuclear power plants generate electricity, and why the atomic world contains such concentrated power. It is a gentle equation, written in just 5 symbols, yet it describes one of the most fundamental truths about the nature of existence. Antimatter particles have opposite charges to their matter counterparts. For every type of matter particle, there exists a mirror image counterpart with the same mass but opposite charge. The electron has the positron, the proton has the antiproton, and the neutron has the antineutron. When Paul Dirac first predicted the existence of antimatter in 1928 through his elegant equation, many physicists were skeptical. But in 1932, Carl Anderson discovered the positron in cosmic ray experiments, confirming that antimatter was real. Antimatter behaves identically to matter in almost every respect, obeying the same physical laws and forming the same types of bonds. An antihydrogen atom would emit the same spectrum of light as a regular hydrogen atom. The great mystery is why the universe appears to contain overwhelmingly more matter than antimatter. If equal amounts had been created in the Big Bang, they should have annihilated completely, leaving nothing but pure energy. Something caused a slight asymmetry favoring matter, and understanding this imbalance remains one of the deepest open questions in physics. Antimatter is produced routinely in particle accelerators and is even used in medical imaging through positron emission tomography. It is a quiet reminder that the universe once held a perfect balance, now mysteriously broken. When matter meets antimatter, they annihilate, converting all mass to energy. When a particle of matter encounters its antimatter counterpart, something extraordinary happens. The two particles vanish entirely, and their combined mass is converted completely into energy in the form of high-energy photons. This process, called annihilation, is the most efficient energy conversion known to physics. 100% of the mass becomes energy, far exceeding the tiny fractions converted in nuclear fission or fusion. When an electron meets a positron, they produce two gamma-ray photons that fly off in opposite directions, each carrying a precise amount of energy determined by the mass of the particles. This signature is used in hospitals around the world in a technique called positron emission tomography, which creates detailed images of the body's internal processes. The amount of energy released in matter-antimatter annihilation is staggering. A single gram of antimatter meeting a single gram of matter would release energy comparable to a small nuclear weapon. Producing antimatter is extraordinarily expensive and difficult, which is why antimatter engines remain firmly in the realm of science fiction for now. The annihilation process is a vivid demonstration that mass is simply concentrated energy, waiting to be released under the right conditions. The Standard Model describes all known fundamental particles and 3 of the 4 forces. The Standard Model of particle physics is one of the most successful scientific theories ever constructed. It provides a comprehensive framework that describes all known fundamental particles and 3 of the 4 fundamental forces: the electromagnetic force, the strong nuclear force, and the weak nuclear force. The theory organizes matter particles into 2 families: quarks, which make up protons and neutrons, and leptons, which include electrons and neutrinos. Each family contains 6 members arranged in 3 generations of increasing mass. The forces between these particles are carried by another class of particles called gauge bosons, including photons for electromagnetism, gluons for the strong force, and the W and Z bosons for the weak force. The Higgs boson, discovered in 2012, completed the predicted particle content of the Standard Model. The theory has been tested to extraordinary precision, correctly predicting the outcomes of countless experiments at particle accelerators around the world. Yet the Standard Model is known to be incomplete. It does not include gravity, does not explain dark matter or dark energy, and leaves several deep questions unanswered. It is a magnificent but unfinished map of nature's deepest architecture. Gravity remains the only fundamental force not yet incorporated into quantum theory. Of the 4 fundamental forces, gravity is the most familiar but the most mysterious at the quantum level. We experience gravity every moment of our lives, feeling it pull us toward the Earth, watching it guide the moon around our planet and the planets around the sun. Einstein's general theory of relativity describes gravity beautifully as the curvature of space-time caused by mass and energy. At large scales, this description works with extraordinary precision. But when physicists try to apply quantum rules to gravity, the mathematics breaks down, producing infinite and meaningless results. The other 3 forces have been successfully described within the quantum framework of the Standard Model, but gravity stubbornly resists. A quantum theory of gravity would need to describe the force in terms of particles called gravitons, but no one has yet observed a graviton or produced a consistent mathematical theory that includes them. Unifying gravity with quantum mechanics is one of the greatest unsolved challenges in all of physics. String theory and loop quantum gravity are among the leading candidates for a solution, but neither has been experimentally confirmed. The quiet pull you feel holding you in your bed tonight is governed by a force whose deepest nature remains one of science's most beautiful mysteries. String theory proposes that fundamental particles are tiny vibrating strings of energy. At the very foundation of matter, string theory suggests something profoundly elegant. Instead of being point-like objects with no internal structure, the fundamental particles may actually be tiny one-dimensional loops or strands of energy, vibrating at specific frequencies. Just as a violin string produces different musical notes depending on how it vibrates, these fundamental strings would produce different particles depending on their vibrational pattern. One pattern might give rise to an electron, another to a quark, and yet another to a photon. In this picture, the diversity of particles in the universe comes down to the different ways a single type of object can vibrate. String theory naturally includes gravity in its framework, something the standard model cannot achieve, because one particular vibrational mode corresponds to the graviton. However, the mathematics of string theory requires extra dimensions of space beyond the 3 we observe, typically requiring 10 or 11 dimensions in total. The extra dimensions are thought to be curled up so tightly that they are far too small for any current experiment to detect. String theory remains unproven and deeply debated, but its mathematical beauty continues to attract some of the most brilliant minds in physics to explore its possibilities. Extra dimensions may exist curled up at scales too small for current instruments to detect. Our everyday experience includes 3 dimensions of space: length, width, and height. We move freely through these directions, and they define the geometry of everything we see. But several theories in modern physics, most notably string theory, predict that additional spatial dimensions exist beyond the 3 we know. These extra dimensions would not be infinite and open like the ones we experience. Instead, they would be curled up or compactified at sizes so extraordinarily small that they lie far beyond the reach of even our most powerful instruments. One common analogy imagines a garden hose viewed from a great distance. The hose appears to be a simple one-dimensional line, but up close, you can see it has a small circular cross-section, a second dimension curled around itself. Similarly, extra dimensions might be wrapped around themselves at every point in space, too tiny to detect directly. Their precise shape and size could determine the properties of particles and forces in our visible universe. Some theoretical frameworks suggest that gravity might behave differently in these hidden dimensions, which could explain why it is so much weaker than the other forces. The search for evidence of extra dimensions continues at the frontiers of experimental physics. The Large Hadron Collider recreates conditions similar to moments after the Big Bang. Beneath the border between Switzerland and France lies the most powerful particle accelerator ever built. The Large Hadron Collider is a circular tunnel roughly 27 kilometers in circumference, buried 100 meters underground. Inside this tunnel, beams of protons are accelerated to nearly the speed of light and then steered into head-on collisions with each other. The energy concentrated in these collisions is so immense that it recreates conditions that existed only a tiny fraction of a second after the Big Bang, when the universe was an incredibly hot, dense soup of fundamental particles. By studying what emerges from these collisions, physicists can learn about the building blocks of matter and the forces that govern them. The collider's most celebrated achievement was the discovery of the Higgs boson in 2012, confirming a theory that had waited nearly half a century for experimental proof. Thousands of scientists from over 100 countries collaborate on experiments at the collider, making it one of the largest scientific endeavors in human history. The machine operates at temperatures colder than outer space and uses superconducting magnets to guide the proton beams with exquisite precision. It is humanity's most ambitious attempt to understand the atoms that compose all things. The discovery of the Higgs boson confirmed the mechanism that gives particles mass. For nearly 5 decades, physicists theorized that an invisible field permeates all of space and interacts with fundamental particles to give them mass. The quantum excitation of this field, a particle known as the Higgs boson, was predicted but remained elusive for decades because it requires enormous energy to produce. On the 4th of July, 2012, scientists at the Large Hadron Collider announced they had found a new particle consistent with the predicted Higgs boson. 2 independent experiments, ATLAS and CMS, each observed the particle independently, providing strong confirmation. The discovery was awarded the Nobel Prize in Physics in 2013, shared by Peter Higgs and Francois Englert, 2 of the theorists who had first proposed the mechanism in the 1960s. Finding the Higgs boson was the culmination of one of the longest and most expensive searches in the history of science. Its existence confirms that the mass of fundamental particles is not an intrinsic property, but rather arises from their interaction with the Higgs field. Without this interaction, particles would be massless, and the universe, as we know it, could not exist. The Higgs boson is the quiet keystone that holds our understanding of particle physics together. Dark matter is thought to be made of particles that do not interact with light. Astronomers have discovered that the visible matter in the universe, all the stars, planets, gas, and dust we can see, makes up only about 5% of the total mass and energy content. Roughly 27% consists of a mysterious substance known as dark matter. Dark matter does not emit, absorb, or reflect light, making it completely invisible to telescopes that detect electromagnetic radiation. Its existence is inferred from gravitational effects. Galaxies rotate faster than they should based on their visible mass alone, and clusters of galaxies bend light from distant objects more strongly than their visible matter can account for. These observations point to vast amounts of unseen mass surrounding galaxies in enormous halos. The leading candidates for dark matter particles include weakly interacting massive particles and axions, but despite decades of searching, no dark matter particle has been directly detected in a laboratory. Underground detectors shielded from cosmic rays, space-based observatories, and particle collider experiments all continue the hunt. Whatever dark matter turns out to be, it represents a humbling reminder that the atoms we have explored tonight make up only a small fraction of what the universe contains. Most of reality remains hidden and waiting to be understood. Dark energy drives the accelerating expansion of the universe through unknown mechanisms. In 1998, 2 teams of astronomers made a startling discovery that would change our understanding of the cosmos. By observing distant supernovae, they found that the expansion of the universe is not slowing down as expected, but is actually accelerating. Something is pushing the fabric of space apart at an ever-increasing rate. This mysterious force was given the name dark energy, and it is estimated to make up roughly 68% of the total energy content of the universe. Unlike dark matter, which pulls things together through gravity, dark energy appears to exert a repulsive pressure that drives space itself to expand faster over time. Its nature remains one of the deepest mysteries in all of physics. Some theories suggest dark energy is a property of empty space itself, related to the energy of the quantum vacuum. Others propose it is a new field that pervades the cosmos, sometimes called quintessence. The discovery earned the 2011 Nobel Prize in Physics, yet we still understand almost nothing about what dark energy actually is. It is a humbling thought that the force shaping the ultimate fate of the universe is something we can barely begin to describe, a vast and quiet mystery surrounding every atom in existence. Neutrinos are ghostly particles that pass through matter almost without interacting. Of all the particles known to physics, neutrinos are among the most elusive. They have incredibly tiny masses, carry no electric charge, and interact with matter only through the weak nuclear force and gravity, both of which are negligibly feeble at the scale of individual particles. This means neutrinos can pass through entire planets without touching a single atom. A neutrino released from a nuclear reaction in the Sun can travel through the Earth's entire diameter as easily as a beam of light passes through a pane of glass. Detecting neutrinos requires enormous instruments buried deep underground to shield them from other particles, and even then, only a handful of the trillions passing through are caught. There are 3 known types of neutrinos, each associated with a different lepton: the electron neutrino, the muon neutrino, and the tau neutrino. One of their most remarkable properties is the ability to oscillate between these types as they travel, a discovery that proved neutrinos have mass and earned the 2015 Nobel Prize in Physics. Neutrinos carry information about processes hidden from light, such as the nuclear reactions deep inside stars. They are the universe's quietest messengers, slipping silently through the night. Billions of neutrinos from the Sun pass through your body every second. Right now, as you rest, an almost inconceivable number of neutrinos are streaming through you. The Sun's core produces vast quantities of neutrinos as a byproduct of the nuclear fusion reactions that generate its light and heat. These solar neutrinos travel outward at nearly the speed of light, and by the time they reach the Earth, about 8 minutes later, they are spread across an enormous volume of space. Yet even so, roughly 65 billion neutrinos pass through every square centimeter of your skin each second. That means trillions are flowing through your entire body at this very moment. You do not feel them because they almost never interact with the atoms you are made of. A neutrino could pass through a wall of lead a light year thick and still have a good chance of emerging on the other side without hitting anything. The fact that so many particles can move through solid matter without consequence is one of the most striking demonstrations of how much empty space exists within atoms themselves. While you sleep, this silent river of neutrinos continues unabated day and night, an invisible stream connecting you directly to the nuclear furnace at the heart of the Sun. Atoms in your body were forged inside stars that exploded billions of years ago. The atoms that compose your body have an extraordinary history stretching back billions of years. Hydrogen, the lightest element, was formed in the first few minutes after the Big Bang. But virtually every heavier element in your body, the carbon in your cells, the nitrogen in your DNA, the calcium in your bones, was created inside the cores of massive stars through nuclear fusion. When those stars exhausted their fuel and collapsed, they exploded as supernovae, scattering their newly forged elements across vast regions of space. Over millions of years, this scattered material gathered together under gravity to form new stars, new planets, and eventually new life. The oxygen you breathe, the phosphorus in your genetic code, and the iron in your blood were all assembled in stellar furnaces that burned out long before the Earth existed. You are quite literally made of star stuff, a phrase coined by the astronomer Carl Sagan that captures this beautiful truth. Every atom in your body has traveled through at least one star, possibly more, before finding its way to you. As you rest tonight, you carry within you the legacy of ancient explosions and the quiet patience of atoms that have journeyed across the cosmos to be part of you. Supernova explosions create heavy elements like gold and uranium. The heaviest elements in the periodic table owe their existence to some of the most violent events in the universe. During a supernova, a massive star collapses and then rebounds in an explosion of almost unimaginable power, releasing more energy in a few seconds than the sun will produce in its entire lifetime. In the extreme temperatures and pressures of this explosion, neutrons are captured by atomic nuclei at rapid rates, building up heavier and heavier elements in a process called rapid neutron capture, or the R process. This is how elements like gold, platinum, uranium, and many others are formed. Without supernovae, the universe would contain only the lightest elements produced in the Big Bang and ordinary stellar fusion. Recent observations have also confirmed that neutron-star mergers, the collision of two incredibly dense stellar remnants, produce heavy elements in much the same way. The gold in any ring or necklace, the uranium that powers nuclear reactors, and the platinum in catalytic converters were all created in these cosmic cataclysms. It is a remarkable thought that the rarest and most precious materials on Earth were born in the death throes of stars far larger and older than our Sun. The atoms of these elements have traveled immense distances to reach our quiet world. The iron in your blood was created in the cores of massive dying stars. Iron holds a special place in the story of atoms and stars. It is the heaviest element that can be produced through ordinary nuclear fusion inside a star, because fusing iron does not release energy, but rather absorbs it. When a massive star has built up a core of iron through successive rounds of fusion, it has reached the end of its energy-producing life. The iron core collapses under gravity, triggering a supernova explosion that scatters the star's contents across space. The iron atoms released in that explosion eventually become part of gas clouds, new stars, planets, and living organisms. The hemoglobin molecules in your red blood cells each contain iron atoms at their centers, and it is these atoms that bind to oxygen and carry it through your bloodstream to every cell in your body. Each of those iron atoms was forged in the heart of a massive star that died long before the Earth was born. When you feel your pulse, you are feeling the rhythm of iron atoms at work, atoms that once sat at the center of a stellar core. It is a gentle and humbling connection between your body and the life cycles of the largest objects in the cosmos, written in the quiet chemistry of your own blood. Hydrogen is the simplest and most abundant element in the universe. Hydrogen is where the story of atoms begins. With just one proton and one electron, it is the simplest element in the periodic table and by far the most abundant in the cosmos. Roughly 75% of all ordinary matter in the universe is hydrogen by mass. It was the first element to form after the Big Bang, emerging from the primordial soup of particles as the universe cooled in its earliest minutes. Hydrogen atoms eventually gathered together under gravity to form the first stars, where they began fusing into helium and heavier elements. Today, hydrogen remains the primary fuel of every star, including our Sun, which converts roughly 600 million tons of hydrogen into helium each second. On Earth, hydrogen is most commonly found bonded to oxygen in water molecules, making it essential to every living thing. The simplicity of hydrogen belies its importance. It is the starting point for all stellar nucleosynthesis, the source of the universe's primary energy process, and a building block of water, acids, and countless organic molecules. Despite being the lightest and simplest atom, hydrogen is arguably the most significant element in existence, quietly fueling the cosmos and sustaining life. The human body contains roughly 7 octillion atoms working together. The number of atoms in a human body is almost beyond comprehension. An average adult contains approximately 7 octillion atoms, which is a 7 followed by 27 zeros. The vast majority of these are hydrogen, oxygen, and carbon, the three elements that form the basis of water and organic molecules. Nitrogen, calcium, phosphorus, and several other elements make up most of the remainder. These atoms are not randomly scattered, but organized into an intricate hierarchy of molecules, cells, tissues, and organs, each performing specific functions with extraordinary coordination. A single cell in your body contains roughly 100 trillion atoms working together to maintain the processes of life. Yet not a single one of those atoms is permanent. Over approximately 7 to 10 years, nearly every atom in your body is replaced through the ongoing processes of eating, breathing, drinking, and excretion. The atoms you are made of right now are not the same ones you were made of a decade ago. Your physical identity is a pattern maintained by biology rather than a fixed collection of matter. It is a gentle truth that the atoms composing you tonight are merely passing through, borrowed briefly from the earth and destined to return, only to be gathered again by something else entirely. Atoms are constantly vibrating, even at temperatures approaching absolute zero. Temperature at the atomic level is a measure of how much the atoms and molecules in a substance are vibrating. The hotter something is, the more vigorously its atoms move. As temperatures drop, atomic vibrations slow down, but they never stop entirely. Even at temperatures very close to absolute zero, the coldest possible temperature, atoms retain a residual amount of motion known as zero-point energy. This is a direct consequence of the uncertainty principle. If an atom were completely still, its position and momentum would both be precisely known, which quantum mechanics forbids. The zero-point energy is the minimum amount of energy a quantum system can possess, and it ensures that atoms are always gently trembling, even in the coldest conditions the universe can offer. This residual motion has real physical consequences, contributing to phenomena like superfluidity and preventing certain substances from freezing solid even at the lowest achievable temperatures. Helium, for example, remains liquid all the way down to absolute zero under normal pressure precisely because of this quantum vibration. As you rest tonight, the atoms in your body are vibrating with thermal energy far above zero point, carrying the gentle warmth that sustains you through the quiet hours. Absolute zero is the theoretical temperature where atomic motion reaches its minimum. Absolute zero represents the lowest possible temperature in the universe, the point at which atomic motion is reduced to its quantum mechanical minimum. On the Kelvin scale, it is 0 kelvins, which corresponds to roughly minus 273.15 degrees Celsius. At this temperature, a perfect classical system would have no thermal energy whatsoever, and all motion would cease. In reality, quantum mechanics ensures that a faint residual vibration always remains, but absolute zero is nonetheless the theoretical floor. No laboratory has ever reached absolute zero precisely, though experiments have come extraordinarily close, cooling atoms to within billionths of a degree. At these ultra-cold temperatures, matter begins to behave in ways that have no counterpart in everyday experience. Gases that normally bounce and flow become still and orderly. Quantum effects that are usually hidden at room temperature become visible and dominant. The pursuit of absolute zero has led to some of the most remarkable discoveries in physics, including superconductivity, superfluidity, and Bose-Einstein condensation. It is a boundary that nature allows us to approach, but never quite cross, a quiet limit woven into the laws of physics that gently reminds us the universe always keeps its final secrets. Bose-Einstein condensates form when atoms are cooled to near absolute zero. When certain types of atoms are cooled to temperatures just a fraction of a degree above absolute zero, something extraordinary happens. The individual atoms lose their separate identities and merge into a single quantum entity, behaving as one unified wave rather than a collection of distinct particles. This state of matter is called a Bose-Einstein condensate, predicted by Satyendra Nath Bose and Albert Einstein in the 1920s, but not created in a laboratory until 1995. The achievement earned Eric Cornell, Carl Wieman, and Wolfgang Kettel the Nobel Prize in Physics in 2001. In a Bose-Einstein condensate, quantum behavior that is normally confined to the subatomic world becomes visible at scales large enough to observe directly. The condensate acts as a superatom, with all its constituent atoms occupying the same quantum state simultaneously. This makes it an ideal system for studying fundamental quantum phenomena in a controlled setting. Scientists have used condensates to slow light to simulate conditions in the early universe, and explore the boundary between quantum and classical worlds. The Bose-Einstein condensate is one of the most exotic states of matter ever created, a quiet triumph of physics that reveals what atoms can become when the noise of thermal energy is stripped almost entirely away. At ultra-cold temperatures, atoms can behave as a single quantum entity. Under everyday conditions, atoms behave as distinct individual particles, each following its own path and carrying its own energy. But when atoms are cooled to temperatures within billionths of a degree of absolute zero, the quantum wave functions of individual atoms begin to overlap and merge. The atoms lose their individual identities and start behaving collectively as though they were a single enormous quantum object. This phenomenon occurs because at such low temperatures, the wavelength associated with each atom becomes large enough to overlap with its neighbors, blurring the boundaries between them. In this state, thousands or even millions of atoms move in perfect unison, responding to disturbances as one coherent wave. It is as though a crowded room of people suddenly began to breathe, walk, and think in perfect synchrony. This collective quantum behavior gives rise to remarkable phenomena such as superfluidity and superconductivity, where resistance and friction vanish entirely. Studying these ultra-cold systems gives physicists a window into quantum mechanics at scales normally too small to observe. The transformation from many separate atoms into one unified quantum entity is among the most profound demonstrations that the quantum world operates by rules entirely unlike our daily experience. Superfluidity allows certain substances to flow without any friction. When liquid helium is cooled below about 2.2 kelvins, it undergoes a remarkable transformation. It becomes a superfluid, a state of matter in which the liquid flows with absolutely zero viscosity. A superfluid can creep up the sides of a container, pass through tiny pores that would block any normal liquid, and flow in a loop indefinitely without ever slowing down. This bizarre behavior arises because a significant fraction of the helium atoms enter the same quantum ground state, forming a macroscopic quantum phenomenon. In its superfluid state, helium-4 is described by a single wave function that governs the motion of the entire liquid. Any attempt to slow the fluid would require breaking it out of this quantum state, which requires a minimum amount of energy. Below that threshold, the fluid simply cannot lose energy to friction. Superfluidity has also been observed in helium-3 and in ultra-cold atomic gases, confirming that it is a general quantum phenomenon rather than a quirk of one particular substance. Scientists believe that superfluidity may also occur in the dense interiors of neutron stars, where neutrons form pairs that flow without resistance through the stellar core. It is one of the quietest and most beautiful demonstrations of quantum mechanics at work in the physical world. Superconductors conduct electricity with zero resistance at low temperatures. In most materials, electrical resistance converts some of the flowing current into heat, which is why wires grow warm when they carry electricity. But in certain materials cooled below a critical temperature, resistance vanishes completely and electricity flows without any loss of energy whatsoever. These materials are called superconductors, and the phenomenon was first discovered in mercury in 1911 by the Dutch physicist Heike Kamerlingh-Onnes. In a superconductor, electrons pair up into structures called Cooper pairs, which move smoothly through the material's lattice without scattering off imperfections or vibrations. This pairing is a quantum mechanical effect, and it allows electricity to circulate in a superconducting loop indefinitely. Superconductors also expel magnetic fields from their interiors, a phenomenon known as the Meissner effect, which is why a magnet can levitate above a superconductor in striking demonstrations. Today, superconductors are used in MRI machines, particle accelerators, and advanced power transmission systems. Scientists continue to search for materials that can superconduct at higher temperatures, ideally at room temperature, which would revolutionize energy technology. The dream of lossless electrical conduction depends on the quantum behavior of electrons within atoms, a quiet reminder that the tiniest particles hold the key to some of our grandest technological ambitions. Quantum computers use superposition and entanglement to process information. Classical computers store and process information using bits, each of which can be either a 0 or a 1 at any given time. Quantum computers use a fundamentally different unit called a qubit, which exploits the quantum properties of superposition and entanglement to process information in ways that classical machines cannot. A qubit can exist in a superposition of both 0 and 1 simultaneously, and when many qubits are entangled together, the number of possible states grows exponentially. This allows a quantum computer to explore vast numbers of solutions in parallel, potentially solving certain types of problems far more quickly than any classical computer. Tasks such as simulating complex molecules, factoring large numbers, and optimizing logistics could see dramatic speedups on quantum hardware. However, building a practical quantum computer is extraordinarily challenging because qubits are incredibly fragile. Any interaction with the environment can destroy their quantum states in a process called decoherence. Current quantum computers operate at temperatures close to absolute zero and require extreme isolation from external noise. Despite these challenges, progress has been steady, and many researchers believe quantum computing will transform fields ranging from medicine to cryptography. The power of these machines flows directly from the strange quantum properties of atoms and their subatomic components. Qubits can represent both 0 and 1 simultaneously, unlike classical bits. In a classical computer, the fundamental unit of information is the bit, which is always in one of two states, 0 or 1. This binary system underlies all classical computation, from simple addition to streaming video. A qubit, the quantum equivalent, is far more versatile. Thanks to the principle of superposition, a qubit can exist in a combination of 0 and 1 at the same time, weighted by probability amplitudes that determine the likelihood of finding it in either state when measured. Two entangled qubits can represent 4 states simultaneously, 3 can represent 8, and with each additional qubit, the number of simultaneously represented states doubles. A system of just 300 qubits could represent more states than there are atoms in the observable universe. This exponential scaling is what gives quantum computers their potential advantage. However, once a qubit is measured, its superposition collapses to a single definite value, just like any other quantum system. The art of quantum computing lies in manipulating qubits through carefully designed sequences of quantum gates that guide the superposition toward the desired answer before measurement occurs. Qubits are built from various physical systems, including trapped ions, superconducting circuits, and photons, each quietly harnessing the quantum nature of atoms to redefine what computation means. Quantum cryptography uses the laws of physics to create unbreakable encryption. Most modern encryption relies on mathematical problems that are difficult but not impossible to solve. A sufficiently powerful computer could, in principle, crack these codes given enough time. Quantum cryptography takes a fundamentally different approach, basing its security not on mathematical difficulty, but on the laws of physics themselves. The best-known method, called quantum key distribution, uses individual photons to transmit encryption keys between two parties. Because of the no-cloning theorem, a quantum state cannot be perfectly copied without disturbing it. If an eavesdropper tries to intercept and measure the photons during transmission, the act of measurement inevitably alters the quantum states, introducing errors that the legitimate parties can detect. This means any attempt at espionage reveals itself automatically. Quantum key distribution has been demonstrated over optical fibers and even through satellite links spanning thousands of kilometers. As quantum computers advance and threaten to break existing encryption methods, quantum cryptography offers a path toward communication that is secure in principle against any computational attack. It is a technology born directly from the fundamental properties of photons and the quantum rules that govern them, turning the strangeness of the atomic world into a practical shield for sensitive information in an increasingly connected world. Quantum sensors can detect incredibly small changes in magnetic and gravitational fields. The extreme sensitivity of quantum systems to their environment, which makes building quantum computers so difficult, turns out to be an extraordinary advantage when it comes to measurement. Quantum sensors exploit the delicate nature of quantum states to detect changes in physical quantities with a precision far beyond what classical instruments can achieve. Atomic interferometers, for example, use the wave nature of atoms to measure gravitational acceleration with extraordinary accuracy, enabling scientists to detect underground tunnels, mineral deposits, and changes in water tables from the surface. Nitrogen vacancy centers in diamond are being developed as quantum sensors that can detect individual magnetic fields from single electrons, with potential applications in brain imaging and materials science. Superconducting quantum interference devices, known as SQUIDs, measure magnetic fields so faint that they can detect the electrical activity of a single neuron. These sensors work because quantum properties like superposition and entanglement amplify the effect of tiny disturbances, converting them into measurable signals. The same fragility that complicates quantum computing becomes a powerful tool when the goal is sensing rather than computation. Quantum sensors are poised to transform fields from geology to medicine, all by listening carefully to the quantum whispers of individual atoms and particles. Atomic clocks measure time with extraordinary precision using electron transitions. The most accurate timekeeping devices ever built rely on the quantum behavior of atoms. An atomic clock works by tuning a microwave or optical signal to match the exact frequency at which electrons in a specific atom transition between two energy levels. Cesium atomic clocks, which define the international standard for the second, vibrate at exactly 9,192,631,770 cycles per second. This extraordinary precision means that a well-built cesium clock would lose less than 1 second over a period of several hundred million years. More recently, optical clocks using atoms like strontium and ytterbium have achieved even greater accuracy, losing no more than a second in tens of billions of years, a timescale longer than the current age of the universe. This astonishing precision depends on the fact that quantum transitions in atoms are extraordinarily consistent. An electron in one cesium atom transitions at exactly the same frequency as an electron in any other cesium atom anywhere in the universe. Atomic clocks are essential for satellite navigation, telecommunications, and fundamental physics research. They exemplify how the reliable, repeating behavior of atoms at the quantum level provides the foundation for technologies that shape modern civilization. GPS satellites rely on atomic clocks to calculate positions accurately. The global positioning system that guides you through unfamiliar streets and helps airplanes navigate safely across oceans depends fundamentally on the quantum behavior of atoms. Each GPS satellite carries multiple atomic clocks that broadcast time signals toward the Earth. Your GPS receiver picks up signals from several satellites and calculates your position by measuring the tiny differences in the arrival times of those signals. Since the signals travel at the speed of light, even a nanosecond of error in timing translates to roughly 30 centimeters of positional error. The atomic clocks aboard the satellites must therefore be extraordinarily precise. They also require corrections for the effects of Einstein's relativity. Time runs slightly faster on the satellites than on the ground because of the weaker gravitational field at orbital altitude, and slightly slower because of their high orbital velocity. Without accounting for these relativistic effects, GPS positions would drift by roughly 10 kilometers per day, making the system useless. Both quantum mechanics, which makes atomic clocks possible, and general relativity, which predicts how gravity affects time, must work together for the system to function. GPS is one of the most elegant examples of advanced physics quietly serving everyday life, all built upon the predictable quantum transitions of atoms orbiting far above your head. The Copenhagen interpretation suggests reality is undefined until measurement occurs. One of the most influential ways of understanding quantum mechanics is the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s. According to this view, a quantum system does not have definite properties until a measurement forces it to assume a particular state. Before measurement, a particle exists in a superposition of all possible outcomes, described by a wave function. The act of measurement causes this wave function to collapse, and the particle settles into one definite state chosen according to the probabilities encoded in the wave function. The Copenhagen interpretation does not try to explain what the particle is doing between measurements. It simply states that such questions are meaningless because only measured outcomes are real. This stance troubled Einstein deeply, who argued that the physical world must have definite properties whether anyone is looking or not. His famous objection that he refused to believe the moon ceases to exist when no one is looking at it captures the discomfort many feel with this interpretation. Despite these philosophical challenges, the Copenhagen interpretation remains the most widely taught framework for understanding quantum mechanics, and its predictions have never been contradicted by experiment. It is a gentle but radical idea that reality at the atomic level is shaped by the very act of observation. The many worlds interpretation proposes that all quantum outcomes occur in branching universes. If the Copenhagen interpretation troubles you with its suggestion that reality is undefined until observed, the many worlds interpretation offers a radically different picture. Proposed by Hugh Everett III in 1957, this interpretation holds that every possible outcome of a quantum measurement actually occurs, but in separate branching universes that split apart at the moment of measurement. When you measure an electron's spin and find it pointing up, there is another universe in which you measured it pointing down. Both outcomes are equally real. The wave function never collapses in this view. Instead, it evolves smoothly and deterministically, and what we perceive as collapse is simply our awareness being confined to one particular branch. The many worlds interpretation eliminates the need for a special role for the observer, treating measurement as just another physical process. However, it implies an almost inconceivable proliferation of parallel universes, constantly branching at every quantum event throughout the cosmos. Critics find this extravagant, while supporters argue it is the most elegant reading of the mathematics. The many worlds interpretation remains a serious and widely discussed framework in theoretical physics, a quiet suggestion that the universe is far vaster than we can perceive. The measurement problem asks why observation causes wave function collapse. The measurement problem is one of the oldest and most stubborn puzzles in quantum mechanics. The equations of quantum theory describe how a particle's wave function evolves smoothly and predictably over time, spreading out into superpositions of many possible states. Yet whenever a measurement is performed, the wave function seems to collapse abruptly into a single outcome. The problem is that the equations themselves contain nothing that explains when, how, or why this collapse occurs. A measurement is presumably just a physical interaction between the quantum system and the measuring device, and the measuring device is itself made of atoms obeying quantum rules. So why should measurement be special? Different interpretations of quantum mechanics offer different answers. The Copenhagen interpretation simply accepts the collapse as a fundamental process. The many worlds interpretation denies that collapse happens at all. Decoherence theories suggest that the interaction with a complex environment effectively destroys superpositions without any mysterious collapse. Yet none of these fully resolves the issue to everyone's satisfaction. The measurement problem has inspired nearly a century of debate among the finest minds in physics and philosophy. It is a quiet but persistent question at the heart of our most successful physical theory, asking what it truly means for something to be real. Decoherence explains why quantum effects are not observed at everyday scales. If atoms and subatomic particles can exist in superpositions and display interference effects, why do we never see a chair or a cat in two places at once? The answer lies in a process called decoherence. When a quantum system interacts with its surrounding environment, which is made up of countless other atoms and photons, information about its quantum state leaks out into that environment. The delicate phase relationships that allow a superposition to produce interference effects are disrupted almost instantaneously. The system does not technically collapse into a single state, but it behaves as though it has, because the quantum coherence that distinguishes a superposition from an ordinary mixture is lost beyond recovery. This process happens incredibly quickly for large objects. A grain of dust in contact with air molecules loses its quantum coherence in a fraction of a trillionth of a second. This is why the quantum world appears so different from the everyday world. It is not that quantum rules stop applying to large objects, but that the environment destroys quantum effects far too rapidly for us to notice them. Decoherence provides a bridge between the strange quantum world and the familiar classical world, explaining why atoms can behave as waves while the objects they compose cannot. Quantum coherence must be maintained for quantum technologies to function. Quantum technologies such as quantum computers, quantum sensors, and quantum communication systems all depend on maintaining quantum coherence, the delicate state in which quantum superpositions and entanglements remain intact and useful. Coherence allows qubits to exist in superpositions, sensors to detect faint signals, and photons to carry secure encryption keys. But coherence is extraordinarily fragile. Any interaction with the surrounding environment, whether a stray photon, a vibration, or a temperature fluctuation, can destroy the coherence and render the quantum system classical. This is why quantum computers typically operate at temperatures close to absolute zero in carefully shielded vacuum chambers. Even under these extreme conditions, coherence times are limited, and engineers must perform their calculations quickly before decoherence sets in. Extending coherence times is one of the central challenges in quantum technology research. Different physical platforms offer different trade-offs. Superconducting circuits can perform operations very quickly but lose coherence faster, while trapped ions maintain coherence longer but operate more slowly. The race to build practical quantum technologies is fundamentally a race against decoherence, an effort to preserve the delicate quantum nature of atoms and particles long enough to harness their extraordinary capabilities. The observer effect means that measuring a quantum system inevitably disturbs it. In the quantum world, you cannot observe something without changing it. This principle, known as the observer effect, arises because any measurement requires some form of interaction between the measuring apparatus and the system being measured. At the macroscopic level, this effect is typically negligible. Shining a torch on a football does not noticeably change its position or speed, but at the atomic scale, the interaction is significant. To detect an electron, for example, you might bounce a photon off it, but the photon carries enough momentum to alter the electron's path. The more precisely you try to locate the electron by using a shorter wavelength photon with higher energy, the greater the disturbance you cause. The observer effect is related to but distinct from the uncertainty principle, which is a fundamental feature of wave functions rather than a consequence of measurement apparatus. Together, these principles establish that the quantum world is inherently participatory. The act of gaining knowledge about a system changes the system itself. It is a gentle reminder that at the atomic level, observation is never passive. To look is to touch, and to touch is to transform. The universe insists that knowing and changing are, at its deepest level, inseparable acts. Quantum randomness may be truly fundamental rather than a result of hidden causes. In classical physics, randomness is usually a sign of ignorance. A coin flip seems random only because we do not know all the forces acting on the coin. In principle, with enough information, we could predict every toss. But in quantum mechanics, randomness appears to be fundamentally different. When a radioactive atom decays or a photon passes through a beam splitter, the outcome cannot be predicted even with complete knowledge of the system. The probabilities are built into the laws of physics themselves, not into our lack of information. Einstein resisted this idea throughout his life, famously declaring that God does not play dice. He believed there must be hidden variables beneath quantum mechanics that determine outcomes in a deterministic way. But experiments testing Bell's inequalities have consistently shown that no local hidden variable theory can reproduce all the predictions of quantum mechanics. This suggests that quantum randomness is genuine, an irreducible part of how the universe operates. True randomness at the quantum level has practical applications. Quantum random number generators produce sequences that are provably unpredictable, useful in cryptography and secure communications. The quiet unpredictability of atoms is not a limitation, but a fundamental feature of reality, built into the deepest fabric of the world around you. Bell's inequality experiments suggest that hidden variable theories face serious limitations. In 1964, the physicist John Stuart Bell devised an ingenious mathematical inequality that could test whether quantum mechanics was truly random, or whether hidden variables secretly determined the outcomes of experiments. If hidden variables existed and respected locality, meaning no influence could travel faster than light, then the correlations between measurements on entangled particles would have to obey Bell's inequality. Quantum mechanics, however, predicted that certain experiments would violate the inequality, showing stronger correlations than any local hidden variable theory could explain. Starting in the 1980s, a series of increasingly precise experiments confirmed that Bell's inequality is indeed violated, exactly as quantum mechanics predicts. The most comprehensive tests, performed in 2015, closed all major loopholes and won the 2022 Nobel Prize in Physics for Elaine Aspect, John Clauser, and Anton Zeilinger. These results strongly suggest that the quantum world does not operate according to hidden deterministic rules, and that entangled particles share a connection that transcends classical notions of locality. The universe, at its deepest level, appears to contain correlations that have no explanation in terms of pre-existing properties or hidden signals. Bell's theorem is a quiet but revolutionary result that has permanently changed how physicists think about the nature of reality itself. Quantum field theory describes particles as excitations in underlying fields. In the most advanced version of quantum mechanics, known as quantum field theory, particles are not fundamental objects that simply exist. Instead, they are understood as localized excitations, or ripples, in underlying quantum fields that pervade all of space. There is an electron field, a quark field, a photon field, and so on, and what we call a particle is really a quantized vibration in the corresponding field. When energy is added to the electron field, an electron appears. When the energy is removed, the electron vanishes. This framework elegantly unifies quantum mechanics with special relativity and provides the mathematical foundation for the standard model of particle physics. Quantum field theory explains how particles can be created and destroyed in high-energy collisions, something that point particle theories cannot account for. It also naturally incorporates antiparticles, which appear as vibrations in the same field but moving in a specific mathematical direction. The predictions of quantum field theory have been confirmed to extraordinary precision. The magnetic moment of the electron, for instance, agrees with theory to more than 10 decimal places. Quantum field theory paints a picture of the universe as a vast, interwoven tapestry of fields, with particles as fleeting patterns rippling across that tapestry wherever energy gathers. Every type of particle has a corresponding quantum field that fills all space. According to quantum field theory, the universe is not made up of particles scattered through empty space, but of fields that extend everywhere and always. For every known type of particle, there is a corresponding quantum field. The electron field fills all of space, and wherever this field is excited, an electron appears. The photon field fills all of space, and wherever it is excited, a photon exists. The same holds for quarks, neutrinos, the Higgs boson, and every other fundamental particle. These fields do not turn on and off. They are always present, even in regions where no particles are detected. In a perfect vacuum with no particles at all, every quantum field still exists at its minimum energy level, quietly fluctuating due to the uncertainty principle. These zero-point fluctuations are what give rise to virtual particles and the Casimir effect. The strength of a field at a given point determines the probability of finding a particle there. This perspective transforms our understanding of the universe from a collection of objects floating in emptiness to an interlocking web of fields whose vibrations create everything we observe. The chair beneath you, the air around you, and the starlight above you are all patterns of excitation in these silent fields that stretch throughout the cosmos. Vacuum energy contributes to the cosmological constant, affecting cosmic expansion. Even in the emptiest regions of space, the quantum vacuum contains energy. The zero-point fluctuations of all quantum fields contribute a baseline energy density to every cubic meter of the universe. This vacuum energy has a remarkable property. It exerts a negative pressure that acts like a repulsive gravitational force, pushing space apart. In Einstein's equations of general relativity, this vacuum energy corresponds to what is called the cosmological constant, a term that determines whether the universe expands, contracts, or stays the same size. Observations of distant supernovae and the cosmic microwave background suggest that the cosmological constant has a small but positive value, driving the accelerating expansion of the universe. However, when physicists calculate the expected vacuum energy using quantum field theory, the result is enormously larger than the observed value, off by roughly 120 orders of magnitude. This discrepancy, known as the cosmological constant problem, is one of the greatest unsolved puzzles in physics. Something must cancel most of the vacuum energy, leaving only a tiny residue, but no one knows what that mechanism is. The vacuum energy quietly influences the fate of the entire cosmos, yet its true nature remains deeply mysterious, a gentle riddle woven into the emptiness between atoms and stars. The Planck scale represents the smallest meaningful length in physics. At the very bottom of the scale of sizes lies a limit that current physics cannot see beyond. The Planck length, roughly 1.6 times 10 to the power of minus 35 meters, is the scale at which the known laws of physics are expected to break down. It is far smaller than any atomic nucleus, far smaller than a proton, and far smaller than anything ever measured or directly observed. To appreciate how small it is, consider that the Planck length is to a proton what a proton is to a small city. At this scale, the fabric of space and time itself is thought to become grainy and turbulent, dominated by quantum fluctuations of gravity. The Planck length is derived from three fundamental constants: the speed of light, the gravitational constant, and the reduced Planck constant. Together, these define a natural system of units that physicists believe marks the boundary where quantum mechanics and general relativity must merge into a single unified theory. No experiment currently available can probe distances this small, and it may require entirely new physics to understand what happens at the Planck scale. It remains one of the deepest frontiers of human knowledge, a quiet threshold below which the nature of space itself remains unknown. At the Planck scale, quantum effects and gravity become equally important. In most of physics, quantum mechanics and gravity operate in separate domains. Quantum mechanics governs the behavior of atoms and subatomic particles, while gravity shapes the motions of planets, stars, and galaxies. The two theories rarely need to be applied simultaneously because they dominate at vastly different scales. But at the Planck scale, this comfortable separation vanishes. The energies involved are so extreme and the distances so tiny that both quantum effects and gravitational effects become equally strong. This is the regime where physicists expect the smooth fabric of spacetime described by general relativity to break down and reveal a deeper quantum structure. What that structure looks like is one of the greatest open questions in theoretical physics. Attempts to combine quantum mechanics and gravity have led to approaches like string theory and loop quantum gravity, but a complete theory of quantum gravity remains elusive. At the Planck scale, space itself may be discrete rather than continuous, made of tiny units that cannot be divided further. Time, too, may have a minimum tick, the Planck time, roughly 5.4 times 10 to the power of minus 44 seconds. The Planck scale is a quiet reminder that our most successful theories each have boundaries, and that the deepest truths about reality await at the place where those boundaries meet. Loop quantum gravity attempts to quantize spacetime itself. While string theory proposes that fundamental particles are vibrating strings in higher dimensions, loop quantum gravity takes a different approach to the problem of uniting quantum mechanics with gravity. Instead of adding new particles or dimensions, It applies quantum rules directly to the geometry of spacetime itself. In this framework, space is not a smooth, continuous fabric, but is woven from tiny, discrete loops of gravitational field, forming a structure called a spin network. At scales far below an atom, spacetime would resemble a fine mesh or foam rather than a smooth surface. These loops define the smallest possible areas and volumes, creating a natural minimum scale for the universe's geometry. Loop quantum gravity makes the remarkable prediction that space comes in indivisible quanta, just as energy does. This means there is a smallest possible volume of space and a smallest possible area, both on the order of the Planck scale. The theory offers a compelling picture of the Big Bang as a big bounce, suggesting the universe may have contracted from a previous phase before expanding. Loop quantum gravity remains an active area of research, with many of its predictions still awaiting experimental testing. It is a quiet attempt to understand the very fabric from which reality itself is woven. Protons appear to be stable, with lifetimes exceeding the age of the universe. The proton is one of the most enduring particles in the known universe. Experimental observations suggest that protons are either perfectly stable or have lifetimes exceeding 10 to the power of 34 years, a span so inconceivably long that it dwarfs the current age of the universe, which is only about 13.8 billion years. No one has ever observed a proton decay. This extraordinary stability is what allows atoms to persist over cosmic timescales, enabling the existence of matter as we know it. Hydrogen atoms formed in the aftermath of the Big Bang still exist today, their protons intact after nearly 14 billion years. However, some grand unified theories predict that protons should eventually decay, transforming into lighter particles such as positrons and neutral pions. Massive underground detectors filled with thousands of tons of water have been watching for years, hoping to catch a single proton in the act of decaying, but none has been found so far. If proton decay is ever discovered, it would be a landmark achievement, pointing toward physics beyond the standard model. For now, the proton's remarkable stability remains one of nature's quiet guarantees, ensuring that the atoms within you tonight will endure far longer than the stars that created them. Neutrons outside an atomic nucleus decay in about 15 minutes. While protons appear to last essentially forever, neutrons tell a very different story when they are not safely bound inside a nucleus. A free neutron, one that has been released from an atomic nucleus, is unstable and will undergo beta decay with an average lifetime of roughly 14 minutes and 42 seconds. During this process, the neutron transforms into a proton, emitting an electron and an antineutrino in the process. This decay is governed by the weak nuclear force, the same force responsible for certain types of radioactivity. Inside a nucleus, however, neutrons can be perfectly stable because the binding energy they share with neighboring protons and neutrons prevents the decay from occurring. The exact lifetime of the free neutron is actually the subject of ongoing precision experiments because different measurement methods yield slightly different values, a discrepancy that has intrigued physicists and may hint at undiscovered physics. Understanding the neutron lifetime is important for cosmology as well, because it influences how much helium was produced in the first few minutes after the Big Bang. The contrast between the proton's apparent immortality and the neutron's fragility outside the nucleus is one of the quiet surprises of the atomic world, showing how context can dramatically change a particle's fate. The Pauli exclusion principle prevents identical fermions from occupying the same quantum state. In 1925, Wolfgang Pauli proposed a principle that would become one of the cornerstones of atomic physics. The exclusion principle states that no two identical fermions particles such as electrons, protons, or neutrons can occupy the same quantum state simultaneously. This means that in an atom, every electron must differ from every other electron in at least one quantum number, such as its energy level, orbital shape, orientation, or spin direction. This principle is the reason electrons arrange themselves into distinct shells and subshells around the nucleus rather than all piling into the lowest energy level. Without the Pauli exclusion principle, all electrons would collapse into the ground state. Atoms would be far smaller and have very different properties, and the rich chemical diversity of the periodic table would not exist. The exclusion principle also explains the stability of matter. It prevents atoms from being compressed beyond a certain limit, which is what supports white dwarf stars against gravitational collapse. It is responsible for the electronic structure of metals, the band structure of semiconductors, and ultimately the material properties of everything you touch. The Pauli exclusion principle is a quiet but absolute rule that shapes the architecture of every atom and every molecule in existence. Electron spin is an intrinsic property with no classical equivalent. Every electron possesses a property called spin, which contributes to its angular momentum and its magnetic behavior. But despite the name, the electron is not actually spinning like a tiny top. Spin is an intrinsic quantum property that has no analog in classical physics. An electron always has a spin of 1/2, and when measured along any axis, it can only be found in one of two states, spin up or spin down. There are no intermediate values. This two-valued nature of electron spin is what gives rise to the magnetic properties of materials, because each spinning electron acts like a tiny magnet. When the spins of many electrons in a material align, the result is the macroscopic magnetism we observe in everyday magnets. Spin also plays a crucial role in the Pauli exclusion principle. Two electrons can share the same orbital only if they have opposite spins, one up and one down. The Stern-Gerlach experiment, first performed in 1922, provided dramatic evidence of spin quantization by showing that a beam of silver atoms split into exactly two paths when passing through a non-uniform magnetic field. Electron spin is a beautifully strange property, something that every electron possesses yet no classical picture can fully capture, a quiet quantum mystery at the heart of matter. Fermions include electrons, protons, and neutrons, while bosons carry forces. All fundamental particles in nature fall into one of two broad categories, fermions and bosons. Fermions are the particles that make up matter. They include electrons, quarks, protons, neutrons, and neutrinos. Fermions obey the Pauli exclusion principle, meaning no two identical fermions can occupy the same quantum state at the same time. This is what gives matter its structure, preventing atoms from collapsing and giving rise to the different electron shells that define chemistry. Bosons, on the other hand, are the particles that carry forces. Photons carry the electromagnetic force, gluons carry the strong force, and the W and Z bosons carry the weak force. The Higgs boson is associated with the Higgs field that gives particles mass. Unlike fermions, bosons do not obey the exclusion principle. Multiple bosons can occupy the same quantum state simultaneously, which is what allows laser light to be so intense, with trillions of photons all marching in step. The distinction between fermions and bosons comes down to a quantum property called spin. Fermions have half-integer spin values, while bosons have integer spin values. This simple mathematical difference leads to profoundly different physical behavior. The interplay between fermions and bosons is what constructs atoms, enables chemistry, and generates the forces that hold the universe together. The photoelectric effect demonstrated that light comes in discrete packets called photons. In the late 19th century, physicists were puzzled by an experiment that classical wave theory could not explain. When ultraviolet light was shown onto a metal surface, electrons were ejected from the metal. Increasing the brightness of the light increased the number of ejected electrons, but not their energy. Increasing the frequency of the light, however, did increase the energy of each ejected electron. Classical wave theory predicted that brighter light should give each electron more energy, regardless of frequency, but this was not what happened. In 1905, Albert Einstein provided the explanation. Light is not a continuous wave, but comes in discrete packets of energy called photons. Each photon carries energy proportional to its frequency, and a single photon transfers its energy to a single electron. If the photon's energy exceeds the binding energy of the electron is ejected. If not, nothing happens, no matter how many low-energy photons strike the surface. This insight earned Einstein the Nobel Prize in Physics in 1921 and helped launch the quantum revolution. The photoelectric effect was one of the first clear demonstrations that energy at the atomic level is quantized, arriving in indivisible portions rather than flowing as a smooth, continuous stream. Max Planck introduced the concept of energy quanta in 1900. At the turn of the 20th century, physicists faced a deep problem. Classical physics predicted that a heated body should radiate infinite energy at short wavelengths, a result known as the ultraviolet catastrophe. This clearly did not happen in reality, and no one could explain why. In 1900, Max Planck found a solution by making a radical assumption. Energy is not emitted or absorbed continuously, but in discrete packets, which he called quanta. Each quantum of energy is proportional to the frequency of the radiation, connected by a new constant that now bears his name, Planck's constant. This tiny number, roughly 6.6 times 10 to the power of minus 34 joule seconds, sets the scale for all quantum phenomena. Planck himself was uneasy with his own idea, viewing it as a mathematical trick rather than a reflection of physical reality. But subsequent discoveries, including Einstein's explanation of the photoelectric effect and Bohr's model of the atom, confirmed that quantization is indeed fundamental to nature. Planck's constant appears in virtually every equation of quantum mechanics, governing everything from the energy levels of atoms to the uncertainty principle. Max Planck's quiet insight at the dawn of a new century opened the door to an entirely new understanding of the universe at its smallest scales. Niels Bohr proposed that electrons occupy specific quantized energy levels. In 1913, the Danish physicist Niels Bohr introduced a model of the atom that bridged the gap between classical physics and the emerging quantum ideas. Bohr proposed that electrons in an atom do not spiral continuously around the nucleus, as classical electrodynamics would predict, but instead occupy only specific, well-defined energy levels. An electron in one of these permitted levels does not radiate energy and can orbit the nucleus indefinitely. It can move to a higher level by absorbing a photon of exactly the right energy, or drop to a lower level by emitting one. The energy differences between levels correspond precisely to the wavelengths of light observed in atomic spectra, neatly explaining the patterns of colored lines that scientists had catalogued for decades. Bohr's model was spectacularly successful for the hydrogen atom, accurately predicting its emission spectrum with remarkable precision. For heavier atoms, the model required refinements that would eventually lead to the full quantum mechanical treatment. Despite its limitations, Bohr's insight that energy within atoms is quantized was a turning point in physics. He received the Nobel Prize in 1922 for this work. The idea that electrons are confined to specific levels gave the first clear picture of atomic structure and laid the foundation for all that followed in quantum theory. Louis de Broglie suggested that all matter has wave-like properties. In 1924, A young French physicist named Louis de Broglie made one of the boldest proposals in the history of science. He suggested that if light, which was known to be a wave, could also behave as particles, then perhaps particles of matter could also behave as waves. De Broglie derived a simple relationship. The wavelength of any particle is inversely proportional to its momentum. For everyday objects like a tennis ball or a person, the associated wavelength is so incredibly small that it has no observable effect. But for tiny particles like electrons, the wavelength becomes significant and leads to measurable consequences. This hypothesis was confirmed experimentally within a few years when Clinton Davison and Lester Germer showed that electrons fired at a crystal produced diffraction patterns identical to those produced by waves. De Broglie received the Nobel Prize in Physics in 1929 for this insight. His idea became one of the pillars of quantum mechanics, leading directly to the development of wave functions and the Schrödinger equation. The notion that every particle has an associated wave transformed our understanding of the atomic world and opened the door to electron microscopy and many other technologies. It is one of the most profound, quiet truths in physics. Matter is never purely solid, but always partly a wave. Electron microscopes use the wave nature of electrons to image tiny structures. Conventional optical microscopes use light to illuminate specimens, but they are limited by the wavelength of visible light. Features smaller than roughly 200 nanometers cannot be resolved no matter how good the lenses are. Electron microscopes overcome this limitation by using beams of electrons instead of light. Because electrons have much shorter wavelengths than visible photons, they can reveal details thousands of times finer. A transmission electron microscope fires a beam of electrons through an ultra-thin sample, and the pattern of transmitted electrons reveals internal structures at the atomic scale. A scanning electron microscope sweeps a focused beam across the surface of a sample, building up a detailed three-dimensional image of its topography. The development of electron microscopy was made possible by de Broglie's insight that particles have wave-like properties, and by the engineering achievement of controlling and focusing electron beams using electromagnetic lenses. Electron microscopes have revealed the intricate structures of viruses, the crystal lattices of metals, and even the arrangement of individual atoms on surfaces. They have become indispensable tools in biology, materials science, and nanotechnology. Every stunning image of a virus or a nanostructure you have ever seen is a quiet testament to the wave nature of the electron and the quantum principles that govern the atomic world. Semiconductors rely on the quantum behavior of electrons to function. Semiconductors are materials that conduct electricity better than insulators, but less freely than metals, and this intermediate behavior makes them extraordinarily useful. Silicon and germanium are among the most common semiconductor materials. Their conductivity can be precisely controlled by adding tiny amounts of other elements, a process called doping, which introduces extra electrons or creates electron vacancies known as holes. The behavior of electrons in semiconductors is governed entirely by quantum mechanics. Electrons in a semiconductor occupy energy bands separated by a gap, and the width of this band gap determines the material's electrical properties. When an electron gains enough energy to jump across the gap, it becomes free to conduct electricity. This quantum behavior is the foundation of all modern electronics. Every transistor, every solar cell, every LED, and every computer chip depends on the quantum properties of electrons moving through semiconductor materials. The digital revolution that has transformed virtually every aspect of modern life rests upon our ability to manipulate the quantum states of electrons in these materials with extraordinary precision. Billions of transistors on a single chip perform trillions of operations per second, all governed by the quantum rules that dictate how electrons behave within the crystal lattice of a semiconductor. Transistors control electron flow using quantum mechanical principles. The transistor is perhaps the most important invention of the 20th century, and it works by exploiting the quantum behavior of electrons in semiconductor materials. A transistor acts as a tiny electronic switch or amplifier, controlling the flow of electrons through a circuit. In its simplest form, a transistor has three terminals. A small voltage applied to one terminal controls the much larger flow of current between the other two. This allows transistors to amplify signals and to switch between on and off states, forming the basis of digital logic. The transistor was invented in 1947 at Bell Laboratories by John Bardeen, Walter Brattain, and William Shockley, who shared the Nobel Prize in Physics for their achievement. Since then, transistors have been miniaturized to almost unimaginable scales. Modern computer chips contain billions of transistors, each only a few nanometers across, approaching the size of just a few dozen atoms. At these scales, quantum effects such as tunneling become significant and pose challenges for further miniaturization. Engineers must account for these quantum phenomena in their designs, working at the boundary between classical engineering and quantum physics. The device you may be listening to this on tonight contains billions of transistors, each one quietly directing the flow of electrons through quantum mechanical pathways. Lasers produce coherent light through stimulated emission of photons. The word laser stands for light amplification by stimulated emission of radiation, and the process it describes relies directly on the quantum behavior of atoms. When an atom in an excited state encounters a photon with exactly the right energy, the photon can stimulate the atom to release its stored energy as an identical photon. The new photon has the same frequency, direction, phase, and polarization as the original. This process, called stimulated emission, was first described by Albert Einstein in 1917. In a laser, a large number of atoms are pumped into excited states and then stimulated to emit photons in a cascade, producing a beam of light that is extraordinarily coherent and focused. Unlike ordinary light, which spreads out in all directions with many different frequencies, laser light marches in lockstep, all the photons perfectly aligned. This coherence makes lasers useful in an astonishing range of applications, from reading data on discs and scanning barcodes to performing delicate eye surgery and transmitting information through fiber optic cables. Lasers are also essential tools in scientific research, allowing precise measurements of distances, speeds, and atomic properties. The gentle beam of a laser pointer traces its origin back to the quantum rules governing photons and atoms, a quiet technology born from the strange physics of the very small. MRI machines use the quantum spin of hydrogen nuclei to create medical images. Magnetic resonance imaging, one of the most powerful diagnostic tools in modern medicine, relies on the quantum property of spin possessed by hydrogen nuclei in your body. When a patient is placed inside an MRI machine, a powerful magnetic field causes the spins of hydrogen nuclei throughout the body to align with the field. A pulse of radio waves is then applied, tipping the spins out of alignment. As the nuclei relax back to their equilibrium state, they emit radio signals that vary depending on the type of tissue they are embedded in. By measuring these signals from different locations throughout the body, a computer can construct remarkably detailed images of soft tissues, organs, and structures that are invisible to X-rays. The technique is completely non-invasive, and uses no ionizing radiation, making it safer than many other imaging methods. Different tissues relax at different rates, creating contrast that allows doctors to distinguish between healthy and diseased tissue with extraordinary clarity. MRI has revolutionized the diagnosis of brain conditions, joint injuries, cancers, and heart disease. Every MRI scan is a practical application of quantum spin, harnessing the behavior of individual atomic nuclei to create images that can save lives. It is one of the most remarkable examples of quantum physics, quietly serving human health and well-being. Photosynthesis may use quantum coherence to transfer energy efficiently. Plants, algae, and cyanobacteria have been harvesting sunlight for billions of years, and scientists have discovered that they may use quantum mechanics to do it with remarkable efficiency. When a photon of sunlight strikes a light-harvesting complex in a photosynthetic organism, its energy must travel through a network of molecules to reach the reaction center where it drives the chemistry of life. Classical physics would predict that this energy transfer would be a random walk, bouncing inefficiently from molecule to molecule. But experiments have revealed evidence of quantum coherence in this process, suggesting that the energy can explore multiple pathways simultaneously, like a quantum superposition, and find the most efficient route almost instantly. This quantum speedup could explain why photosynthesis achieves near-perfect energy transfer efficiency under certain conditions, wasting almost none of the absorbed sunlight. The discovery that a biological process might exploit quantum coherence was surprising, because biological systems are warm and noisy environments where quantum effects were expected to be destroyed immediately. Research into quantum effects in photosynthesis continues, and the findings are not yet fully settled. But the possibility that plants have been quietly using quantum mechanics for billions of years before humans even conceived of the idea is a beautiful thought to carry with you as you drift towards sleep. Bird navigation might involve quantum effects in molecules within their eyes. Many species of migratory birds navigate vast distances with an accuracy that has puzzled scientists for decades. One leading hypothesis suggests that birds can sense the Earth's magnetic field using a quantum mechanical process in their eyes. Certain molecules called cryptochromes, found in the retinas of migratory birds, are thought to produce pairs of electrons whose quantum spins are correlated through a process called the radical pair mechanism. When light enters the eye, these electron pairs form, and their behavior is influenced by the angle of the surrounding magnetic field. The quantum coherence of these radical pairs, preserved just long enough despite the warmth and noise of a biological system, may allow the bird to perceive the magnetic field as a visual pattern overlaid on its normal vision. Laboratory experiments have shown that the radical pair mechanism can be sensitive to magnetic fields of the right strength, and disrupting the quantum process with specific wavelengths of light does interfere with birds' navigational abilities. While the full picture is still being assembled, the evidence increasingly points toward a genuine quantum compass operating inside the avian eye. If confirmed, it would mean that evolution discovered and harnessed quantum mechanics long before any human physicist ever wrote an equation. Enzymes may use quantum tunneling to speed up chemical reactions in cells. Enzymes are the molecular machines that accelerate the chemical reactions necessary for life, and some scientists believe they harness quantum tunneling to do their work. In many enzyme-catalyzed reactions, hydrogen atoms or protons must be transferred from one molecule to another. Classically, these particles would need enough energy to overcome the energy barrier separating the two molecules. But quantum tunneling allows the particles to pass through the barrier without ever having enough energy to climb over it. Evidence for tunneling in enzymes comes from experiments measuring the rates of reactions at different temperatures and with different isotopes of hydrogen. When deuterium, which is heavier than hydrogen, is substituted, the reaction rate drops by more than classical models can explain, suggesting that the lighter hydrogen benefits from a greater tunneling probability. Enzymes may have evolved to optimize tunneling by precisely positioning the reacting molecules so that the energy barrier is as narrow and low as possible. This would make the quantum effect more likely and speed up the reaction accordingly. If enzymes truly exploit quantum tunneling, it means that the chemistry of life is not purely classical, but takes advantage of the strange rules governing the atomic world. Your body may be quietly relying on quantum mechanics with every breath you take. The smell of certain molecules may depend on quantum vibrations. The way we perceive smell is usually explained by the shape theory of olfaction, which proposes that a molecule's scent is determined by its shape fitting into specific receptors in the nose, much like a key fitting into a lock. But some scientists have proposed an alternative, the vibrational theory of olfaction. According to this idea, the smell of a molecule depends not only on its shape, but also on the quantum vibrations of its chemical bonds. When a molecule binds to a receptor in the nose, the receptor may detect the frequencies at which the molecule's bonds vibrate, using a process similar to quantum tunneling. This would explain why some molecules with very different shapes smell alike, and why some molecules with similar shapes smell quite different. Experiments with deuterium-substituted molecules, which have the same shape but different vibrational frequencies due to the heavier isotope, have produced mixed results, with some studies supporting the theory and others contradicting it. The vibrational theory remains controversial and is not yet widely accepted, but it represents a fascinating possibility. If the quantum vibrations of atoms within a molecule truly contribute to how we perceive its scent, then the simple act of smelling a flower would be one more example of quantum mechanics quietly touching everyday life. Quantum biology explores how quantum effects influence living organisms. Quantum biology is a relatively young field that investigates whether living systems exploit quantum mechanical phenomena to gain functional advantages. For much of the 20th century, most biologists assumed that quantum effects were irrelevant to life, because biological systems are warm, wet, and noisy, conditions that typically destroy delicate quantum states. But a growing body of evidence suggests that certain biological processes may indeed harness quantum mechanics. Potential examples include quantum coherence in photosynthesis, quantum tunneling in enzyme catalysis, and the radical pair mechanism in avian magnetoreception. Researchers have also explored whether quantum effects play a role in the sense of smell, in genetic mutations, and even in the workings of the brain. The field faces significant challenges because demonstrating that a biological process is truly quantum mechanical rather than merely classical requires careful experiments and rigorous theoretical modeling. Not all proposed quantum biological effects have withstood scrutiny, and the field remains one of active debate. But the central question is compelling. Has evolution discovered ways to exploit the quantum properties of atoms and molecules to create more efficient, more sensitive biological machinery? If the answer is yes, then life itself is deeply intertwined with the quantum world at its most fundamental level. Atoms can be trapped and manipulated individually using optical tweezers. In our everyday experience, atoms are far too small and numerous to handle one by one. But in modern laboratories, scientists can isolate individual atoms and manipulate them with extraordinary precision using a technique called optical tweezers. An optical tweezer uses a tightly focused laser beam to create a tiny gradient of electromagnetic force that can hold a small particle, including a single atom, in place. By adjusting the laser, the atom can be moved, rotated, and positioned with incredible accuracy. The technique was developed by Arthur Ashkin, who was awarded the Nobel Prize in Physics in 2018 for his pioneering work. Optical tweezers have become indispensable tools in both physics and biology. Physicists use them to arrange individual atoms into precise patterns for quantum simulation experiments, creating artificial crystal structures one atom at a time. Biologists use them to study the forces exerted by single molecules and the mechanics of molecular motors within cells. The ability to reach into the atomic world and gently move individual atoms with light is one of the quiet triumphs of modern science, a technology that transforms the relationship between the observer and the observed in the most intimate way imaginable. Scanning tunneling microscopes can image and move individual atoms. The scanning tunneling microscope, invented in 1981 by Gerd Binnig and Heinrich Rohrer at IBM, is one of the most remarkable instruments ever created. It works by bringing an atomically sharp metal tip extremely close to a surface and measuring the quantum tunneling current that flows between them. Because the tunneling current depends exponentially on the distance between the tip and the surface, even tiny variations in height corresponding to individual atoms produce measurable changes in the current. By scanning the tip across the surface and recording the current at each point, a computer can build up an image of the surface with atomic resolution. For the first time in history, scientists could see individual atoms arranged on a surface. But the scanning tunneling microscope can do more than just look. By adjusting the voltage and position of the tip, individual atoms can be picked up and placed in new positions. In 1990, a team at IBM used this technique to spell out the letters of their company name using 35 individual xenon atoms on a nickel surface. This image became one of the most famous in the history of science, a quiet demonstration that humanity had gained the ability to manipulate matter at its most fundamental level. Scientists have spelled words using individual atoms arranged on surfaces. One of the most iconic achievements in nanotechnology occurred in 1990, when researchers at IBM's Almaden Research Center used a scanning tunneling microscope to position 35 individual xenon atoms on a nickel crystal surface, spelling out the 3 letters of their company name. This was the first time in history that humans had deliberately arranged individual atoms to create a visible pattern. The image was widely reproduced and became a symbol of the emerging age of nanotechnology. Since then, numerous other atomic-scale images and structures have been created using similar techniques, including corrals of atoms that confine electron waves into beautiful standing wave patterns on metal surfaces. These demonstrations are not merely artistic. They advance our understanding of how atoms interact at surfaces and how electrons behave when confined to extremely small regions. The ability to manipulate individual atoms opens the door to the ultimate miniaturization of devices, with components built from precisely placed atoms. While practical atom-by-atom manufacturing remains a distant goal, the fundamental capability has been demonstrated. Spelling words with atoms is a quiet triumph of human ingenuity, a moment when the boundary between observer and the observed dissolved, and we began to write in the language of atoms themselves. Quantum information treats information as a fundamental aspect of reality. In classical physics, information is an abstract concept imposed by human observers onto physical systems. But in quantum mechanics, information takes on a much deeper significance. The wave function of a quantum system contains all the information that can ever be known about that system, and the laws of quantum mechanics place strict constraints on how information can be created, copied, and destroyed. The no-cloning theorem states that an unknown quantum state cannot be perfectly duplicated, a result with profound implications for security and communication. Quantum information theory studies how information is encoded, transmitted, and processed using quantum systems, and it has revealed deep connections between information, entropy, and the structure of space-time. Some physicists have proposed that information is not merely a human construct, but a fundamental feature of the physical world, perhaps even more fundamental than matter and energy. The black hole information paradox, which asks what happens to information that falls into a black hole, has driven some of the most important advances in theoretical physics in recent decades. The idea that the universe is at its deepest level a vast network of quantum information is one of the most exciting frontiers in modern science, quietly reshaping our understanding of reality from the atomic scale to the cosmic. The atoms you breathe today were once part of dinosaurs and ancient oceans. The atoms that enter your lungs with each breath have been part of an extraordinary number of different things throughout the history of the Earth. Atoms are recycled endlessly through the planet's systems, passing from living organisms to the soil, from the soil to the water, from the water to the atmosphere, and back again. The oxygen atoms you inhale may have once been part of a tree in a carboniferous forest or dissolved in a Jurassic ocean. The nitrogen in your breath may have drifted through the atmosphere while dinosaurs roamed the land below. Some of the carbon atoms in the carbon dioxide you exhale may have been part of a volcanic eruption, a coral reef, or the breath of a creature that lived hundreds of millions of years ago. Because atoms are essentially indestructible under normal conditions, they persist through geological ages, cycling from one form to another without ever being consumed. The same atoms that make up your morning cup of tea have been part of countless other substances and organisms over the eons. It is a quiet and profound connection to the deep history of the planet. Every breath you take tonight links you directly to ancient oceans, ancient forests, and ancient creatures that once shared these same restless atoms. Atoms are recycled endlessly through the Earth systems over geological time. The Earth is a remarkably efficient recycler. Over geological timescales, atoms are continuously exchanged between the atmosphere, the oceans, the rocks, and living organisms in cycles that have been turning for billions of years. The carbon cycle moves carbon atoms from the atmosphere into plants through photosynthesis, from plants into animals through food chains, and back into the atmosphere through respiration and decomposition. The nitrogen cycle converts atmospheric nitrogen into forms usable by living organisms, and then returns it to the air through bacterial action. The water cycle endlessly evaporates, condenses, and precipitates water molecules, carrying their hydrogen and oxygen atoms across the globe. Even the solid rocks beneath your feet are part of this recycling, as plate tectonics slowly draws surface material down into the Earth's mantle and pushes new material up through volcanic activity. The atoms involved in these cycles are not consumed or destroyed. They simply change partners, forming new molecules and joining new structures over and over again. Some of the atoms in your body have cycled through the Earth systems so many times that they have been part of oceans, mountains, forests, and countless organisms over the past 4.5 billion years. It is a gentle testament to the enduring patience of atoms and the planet that endlessly reshuffles them. The quantum world challenges our assumptions about reality and knowledge. The deeper we look into the atomic world, the more our everyday assumptions about reality fall away. We are accustomed to a world where objects have definite positions, where causes precede effects, and where knowing something does not change it. But at the quantum scale, these comfortable certainties dissolve. Particles exist in superpositions until measured. Entangled objects share correlations that cannot be explained by any local mechanism. The act of observation shapes the outcome. Randomness appears to be fundamental rather than a sign of ignorance. These discoveries do not merely add to our knowledge, they fundamentally challenge what we mean by knowledge itself. Quantum mechanics forces us to rethink the relationship between the observer and the observed, between information and reality, between knowing and being. Physicists and philosophers continue to debate what the quantum world truly tells us about the nature of existence, and no consensus has yet been reached. What is clear is that the universe at its smallest scale operates in ways that defy ordinary logic and confound our deepest intuitions. Yet this strange world is the very foundation upon which everything we know and love is built. As you rest tonight, the quantum world continues its mysterious work, holding you together atom by atom in defiance of easy understanding. Understanding atoms reveals a universe far stranger and more beautiful than everyday experience suggests. When you began this journey tonight, the world around you may have seemed solid, predictable, and familiar, but now you have glimpsed what lies beneath that surface. The atoms that compose everything, including you, are mostly empty space held together by forces of astonishing power. Their electrons behave as clouds of probability rather than tiny orbiting spheres. The particles within their nuclei are held by the strongest force in nature, yet the nuclei themselves are unfathomably small. Quantum mechanics governs this hidden world with rules that defy common sense. Superposition, entanglement, tunneling, and the inseparable link between observation and reality. The atoms in your body were forged in stars, scattered by supernovae, and gathered by gravity over billions of years. They have been part of oceans, mountains, forests, and countless other living beings before finding their way to you. And when your time is done, they will continue their journey, patient and indestructible, joining new forms and telling new stories for eons to come. Understanding atoms does not diminish the beauty of the world. It deepens it beyond measure. The universe is far stranger, far more elegant, and far more wonderful than anything our unaided senses can perceive. And that knowledge is a quiet gift to carry into sleep. And now, the quiet wonders of the atomic world begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the invisible building blocks of everything, from the ancient philosophical dream of indivisible particles to the strange quantum realm where certainty dissolves into probability, from the forces that hold nuclei together to the fields that give mass to all things, from the stars that forged your atoms to the technologies that harness quantum principles today. You have explored how atoms are mostly empty space, yet hold all the substance of the world. You have learned that particles can be waves, that observation shapes reality, and that the tiniest scales of nature hold mysteries we are only beginning to understand. You have discovered that the atoms in your body connect you to stars that burned out before our sun was born. You are connected to this story more deeply than you may realize. Right now, as you listen, trillions of atoms are working together to form your thoughts, carry your breath, and keep your heart beating. The same quantum rules that govern particles in far-off laboratories govern the chemistry of your very cells. The story of the atom is your story, written in the language of physics and stretching back to the beginning of time. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle vibration of atoms at rest, like the quiet hum of particles dancing through empty space. Tonight, as you rest, the atoms within you continue their quiet work. They will hold your body together. They will carry signals through your nerves. They will release energy from the food you have eaten. They will build new molecules while you dream, and they will be there when you wake, as they have been since the moment you were born. You are a small, warm arrangement of ancient atoms, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that you are made of the same substance as stars, held together by forces that have shaped the cosmos since time began. Thank you for joining me on this journey through the hidden world of atoms. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of science, nature, and the universe around us. There are more wonders waiting, more secrets hidden in the structure of matter and the depths of quantum physics, more gentle truths to drift through on quiet evenings. Rest well, and may the peaceful mystery of atoms keep you company through the night. This has been Drowsy Discovery. Good night.